The difference between a debugger and a normal program is that the debugger will talk to the operating system and say, I would like to register or attach, I would like to register as the debugger for this other program. The first thing I would say is like print debugging already kind of shows how limited it is, because when you're talking about print debugging, you're thinking of textual logging. Like people are thinking printf. Like I said, a language is not just the language design. It's called a language because it's what people speak.
Hello everyone, welcome to the Game Engineering Podcast. Today I am joined by Ryan Fleury, who is currently working on RAD Debugger, an open source standalone debugger. This project is owned by Epic Games. However, in this 3-hour-long discussion, Ryan is not representing views of his employer, but his own. Now, if you want to know how debuggers work, which means understanding how processes can interact with each other, or what is debug information and how it's generated, strap in and enjoy this highly technical and incredibly interesting deep dive. And now, let's meet Ryan. How have you started programming? What caught your attention in programming? Because this is also an interesting part. And how do you end up in RAD Game Tools and then Epic Game Tools?
Yeah, so I originally started programming maybe to a half serious degree when I was like 6 years old. My older brother showed me QBasic initially, and he was doing like very simple little. It wasn't even like true graphics. It was very janky, like little toy programs, and so he showed me QBasic, and I that exposed me at first to the idea of like a computer is a thing where you can give it a sequence of instructions. I learned about conditionals. I learned about things like this. And that was like my first exposure to programming. And so I had that very early on. And my brother also introduced me to RPG Maker, which people might be familiar with. It's like this I might get this wrong because I never actually played these games, but the old like top-down 2D RPG Final Fantasies, it's basically an engine special case for that type of game. And he showed me that, and it has like a little scripting thing. You don't actually type in any code, but you like add these events, and you can have conditionals, and it is in effect like a visual programming system in a sense. So I did a little bit of that, and I just got super into the idea of designing games at first. And so I did tons of stuff in RPG Maker. I did a little bit of QBasic for a while. I was so interested in RPG Maker because I had played... people who actually have played like the old Final Fantasy games are going to roll their eyes at this, but I had played A Link to the Past, and I loved A Link to the Past. And superficially, they're completely different games. I understand, obviously, like they're totally differently designed, all of that. But superficially, you could see how like 5-6-year-old Ryan would have looked at that and been like, oh, this is the same exact kind of thing.
Yeah.
And so I think that kind of set me up on like an interesting journey, because RPG Maker 2003, for people who don't know, it's like movement is all gridlocked. There's no diagonal movement. The combat is like it's the kind of game where you go to a separate combat screen and it's turn-based and like RPG, right? It's called RPG Maker. Whereas A Link to the Past obviously was like real-time top-down. You're like swinging your sword, bumping into stuff, like that kind of thing. And so I think strangely enough, like that setup kind of set me up for the rest of my entire programming life, because I was trying to recreate experiences like A Link to the Past inside of RPG Maker. And very quickly, when you try to do that, you understand this is not the tool designed for what I'm trying to do. So I think at that point, I kind of understood that at some point I was going to have to move. If I wanted to keep making these games and making these experiences, designing these worlds or whatever, and I wanted more control, then I would have to graduate from RPG Maker at some point. And so fast forward a few years, I kind of got into, there was this like really niche online RPG community that I was involved in. There were like 20 people in the community, but it was based around these games that the sort of organizers of the community had made. And they knowing that I was like a 10-year-old or so kid at the time, they were like, well, we started with Visual Basic, so you should, that's like a good beginner programming kind of situation for you. Of
How
course, at the
old?
time,
How
sorry,
old were they? How old were they in the community?
I believe that the people who were telling me to start with Visual Basic at the time, they were probably like late teens. Like they were using C++ at that point, so they had been doing like more serious game programming for a while. And but they were probably late teens, early 20s, I would think.
Okay. Okay.
So they had made like these actually like actual online RPGs that a handful of people played and actually really loved. And I kind of got into playing those games, and I was like, how did you guys make this? And they said, well, the first game we made it with Visual Basic. So that sent me down this rabbit hole of like Visual Basic programming, which was, I mean, I wouldn't recommend it to people. It's kind of it's kind of a disaster. But I mean, it was probably lower friction for me to get started than C++. But I did get started with C++ like basically a year or two later. But I mean, it was really bad. Like for people who know Visual Basic, it's like it's very tightly integrated into like the sort of the WinForms era of Windows, where you have this WYSIWYG editor for UIs, and you click and drag like buttons onto the window, and like then you can go into the source code and hook up code to the buttons or whatever. And before I learned that you could actually do like true procedural graphics from Visual Basic, like before I even understood what that would mean, I was like literally hand placing picture boxes, which was a specific kind of widget, and I would hand place them onto the window and like in the source code I would move around the picture box procedurally, but then I would use timers in very bizarre ways. I mean, I could probably not where you want this conversation to go. It's kind of ridiculous, but eventually I grew out of that. I was like, I need to learn how to do the, and it also had like major performance problems. So I quickly learned again that was like not the correct tool for the job. Same way as with RPG Maker. And then eventually I got into, after beating my head against the wall like several times, I got into C++ finally. And when I started doing C++, it was very difficult, but eventually I got going with like an Allegro tutorial. Allegro is like sort of like a smaller, older, less comprehensive equivalent to SDL for people who know.
Was this before C++ 11, right? Like,
so I think technically, I don't remember when C++ 11. It's called C++ 11. I don't know if it came out in 2011, but it was probably about that time.
okay.
So 2011 or so. So it probably wasn't out and in the compilers yet. So it was kind of like C++ 03 style programming that I was kind of learning. And people kind of do what you would expect back in that era where Java was so prominent and sort of enterprise object-oriented C++ was so prominent. Like the game programming tutorials would have stuff like virtual functions inside of a class hierarchy. And so, you just pick up patterns when you're a beginner because you don't know how to think through things yet. So I just started kind of copying that, and eventually I kind of got somewhat productive enough to start doing like some amount of programming. I think that my patience was pretty low for like the really C++ stuff, but it was I don't know, how would you say? It was like I was led astray by it to some degree, I guess I would say. But I maintained some degree of productivity and I didn't rat hole on like language stuff really, but
Okay. So we started doing something like visual or graphic things with C++, with Allegro being like a substitute for SDL, or?
Yeah, more or less. I started doing like very simple, just like very simple little games, like starting with, top-down games, moving around collecting coins or whatever, and then moving to like platformers. I did a bunch of platformers, and then throughout that really, and then once I kind of got up and running, I started rapidly like making a bunch of progress, like programming. So I worked on like several games throughout middle and high school in C++, and I actually did build my own online RPG eventually, and it was like real. You could go to a website, download a client, and you would open up a client. It would connect to a server running on my home PC, and it was a full thing.
Nice. In high school. in high
Yeah.
school.
Yeah,
Yeah.
that I put that project to rest at during like sophomore year. It kind of got to the point where it's like, ah man, I don't know. I don't remember exactly what I was feeling at the time, but it was probably like, this isn't gonna turn out too well. Like this code base is getting unwieldy. Not enough people play it. Like it's kind of boring for me. So I put it aside at some point. But I did actually get to a point where I had something called beta, and it was an executable that people could download, which was kind of amazing. But yeah, so I also participated in this extracurricular student organization it's primarily in the United States called Technology Student Association, which TSA for short, but it's not the TSA everyone knows. It's the Technology Student Association, and I did they had a competition where you could build video games, and I would build games every year for that, and every single time it would be like a new engine from scratch. I mean, built with all these libraries and stuff at the time, and still building, not quite like hardcore engine programming yet, but it was like I was building the whole stuff, the level editor, like all that kind of stuff every single time. Because every time I would do it, I would get better, and I was like, oh, I'm not going to keep the old code anymore, like it's all bad. And so I found a lot of rapid iteration through that, participating in that competition. And by junior and senior year of high school, I was doing like first-person 3D games with cinematics and that kind of thing. So that's like
Nice.
that's yeah. So
Nice.
I scaled up, like I feel like pretty well, and it was because of what Mike Acton talked about, which is like just practice, like literally just practice, throwing stuff away, and just iterating on your ability to do stuff. So that was high school, and at the end of high school, I learned about Handmade Hero, which just, I mean, it like took all those layers that I was sort of sitting on top of, and it just tore them all apart, and I just was able to just dig into the meat in a way that was so much more accessible for me. Because obviously, all this information, the information that Casey walks through, especially in the first 30 episodes of Handmade Hero, which is what I always recommend to people, because people would go look at Handmade Hero, they'll say, oh man, there's like 700 episodes, 600 episodes or whatever. He didn't finish the game, so it's like, is this even worth it? How am I going to spend all this time watching this? It's like, just the 30 first episodes are more programming education than you'll probably get in several years at a university computer science curriculum. So it's totally worth it. And
Maybe-
and then oh, go ahead.
Maybe let me interrupt you. For people that don't know, Handmade Hero is a course, or Casey Muratori, a well-known figure in the programming world, have created this project, I think 10 years ago at this point, where he just started from like blank Visual Studio project and was creating a game from scratch. And it was a project that like it started when streaming wasn't even a thing. I think for the platforms then, like there was no Twitch, there was no even Justin TV, which was then turned into Twitch. It was more like you needed to pay to stream, and I think this was like the first coding stream ever. So
Oh wow.
and Casey decided to like, let's show how I would build this, and maybe this would be useful. And I think it sparked careers for people, like
Yeah.
learning through watching episodes of Handmade Hero. People actually tuned in, and like after, let's say, 30 or 40 or 50 episodes, they kind of, okay, now I get it, now I can do something on my own. So Handmade Hero is still available on YouTube on Casey's channel. Yeah, and also you mentioned Mike Acton, which is also a great guy, and his idea to practice, like to, for example, if you have 30 minutes or 1 hour, start something, do something you as much as you can do in this like 60 minutes, and then throw it away, and then start over next time. Like don't do necessarily long projects that would take like months to complete, but start to practice to get good at the craft you're trying to get good at. Okay.
Yeah. I didn't quite follow that advice of doing 60 minutes of programming. I did the months-long projects thing, but I did several of them. I probably did a handful of like shorter projects in there too, but so I didn't quite do the hardcore like asteroids from scratch in 60 minutes or whatever. But but that Mike Acton referenced at some point. But I did get a lot of practice out of it. But so
Handmade Hero, 30. You said like after 30 episodes, you felt comfortable to go and apply these in your projects. This is where I interrupted. Yeah.
Right. So, after about 30 episodes of Handmade Hero, I felt like I could. The entire series is indexed for people who don't know, so you can search through the whole thing. And so once I got to episode 30 or so, I was kind of like, okay, I've done all the basics. We have graphics on the screen, and I'd already done OpenGL and stuff at that point, so I knew a little bit more about graphics programming, but at that point in the series, it's like you've got graphics on the screen, you've got sound coming out, you've got a hot reloading system, which I did not even realize was possible before watching the series. And again, like I was saying, all of this information is accessible out there. Like, you can learn how DLLs are loaded. You could think about the idea of, building your game in DLL separately and hot reloading it. You could think about software rendering, and just talking down. You could learn about all the native APIs, but just the way that Casey did it was so much more accessible to me. So I immediately got hooked on it. I had all the C++ code at the time that was sort of written in the old way that I knew how to write C++. And I guess I didn't quite jump in day one Handmade Hero. I sort of saw some of Casey's rants, and they started making me question things. So I was like, he had videos, or he didn't post these videos, but some other people posted clips of him ranting about how getters and setters for everything is just kind of a waste of everyone's time, or how new and delete versus malloc and free, and talking about how C++ added all of these layers to the problem that new and delete were invented to sort of they were invented to bind initialization and allocation together. And he started breaking these things down for me, and I was kind of like, oh man, maybe he seems to know what he's doing. I feel like I don't feel completely solid in my understanding of programming. And he says all these things are kind of a waste of time, and it kind of feels like they are to me. It feels like every time I add a getter and setter for every field in a structure, it kind of feels like I'm wasting my time. But I heard somewhere that it's good software engineering practice, and so I just did it without thinking about it. And so first I started I just started questioning things, and then at some point I was like, okay, screw my old code base. Let's jump in at day one Handmade Hero and see actually how he does things. And yeah, that completely just revolutionized the way I programmed. And at about day 30, I was like, okay, this is enough for me to go build my own games with now. Because he kind of sketches out all the pieces, input, rendering, and basic 2D software rasterization, and then audio. And then everything else beyond that point is kind of what I could already do. It's just gameplay code, graphics, stuff I knew how to do. And so I took that and started running with it. And so I worked on a game for a few years at that point, using all of that information that I got from Casey. And I ended up eventually showing it publicly, and Casey happened to be there, and he checked it out. And I don't think the game was good design. I ended up eventually abandoning the project because I didn't have a strong enough design backbone to the game. So it was kind of it was extremely high effort for me to design new things and add them into the game, because there were no sort of foundational gameplay systems. It was all very special cased little experiences. And so I showed a 30-minute demo or something like that, and it took so much effort to prepare that 30-minute demo. It did come out fairly well, but it was it would have taken so much more effort to continue the game project after that. So I ended up shelving that project. But Casey liked it enough, and it was a from scratch engine that he recommended me to Jeff. But at this point I was still in college, so I was still I think this was my starting my junior year, or either junior or I think junior year of college. I think it was my junior year of college starting. Or I guess I took 5 years because I did some internships as well. So it was my third year of college, I believe. And so I still had a couple years to go, and I didn't want to drop out because I don't know, maybe it's sunk cost fallacy. People will be like, oh, you should have just dropped out. And maybe they're right. But I didn't want to. I'd put all this time and money into college already. It's like, I should just finish. Also, a lot of companies seem to care about these degrees, even though I didn't really care that much about it. But a lot of people seem to care about it. So if I really needed a job, like, the prudent thing would be, let's get the degree just in case I have to fall back and find some, if I needed a job in big tech, if I wanted to make more money or something like that, then I could actually do that with a degree. Whereas going all in on like my dream job effectively at RAD Game Tools, probably it sounded amazing at the time, but I was like, maybe this is not the right time yet. So, but Jeff actually did email me and he said, do you want to come? It wasn't for the debugger, actually. He was asking if I wanted to come work on telemetry, which is their profiler. And I was like, my heart was shattered because I was like, yes, I absolutely do, but I just really can't right now. But Jeff was totally understanding. He's like, oh yeah, just finish school. We can talk later. So fast forward to 2020, the year that everyone wants to forget.
And Jeff, by the way, is CEO of RAD Game Tools. Just to mention that, right?
Yeah. So my understanding of the company structure. So I came into it way late. In fact, when I joined, it wasn't even RAD anymore because they were bought by Epic. But I'm still kind of in the RAD like sub organization. But my understanding is he co-owned it with at least the Mitch, who's the business. He oversees all the business operations, and then there could have been a third owner. I'm not sure, but I don't want to say that. I don't know the exact company structure. But point is, it was Jeff kind of overseeing the tech, Mitch overseeing the business, and then there might have been like operations and stuff too. But yeah, so he at least co-owned RAD Game Tools, and so where was I? Yeah, so 2020, I had just finished, or I was in the middle of an internship. So I had done a few internships. I did one at Google, actually for Google Stadia, for people who remember that. I did that in 2018, and I actually worked on a pretty interesting project, but I don't think it ever like was used or anything. I did like depth-based reprojection, basically to minimize latency for Google Stadia. I'll comment on this. You can edit this out if it doesn't matter, but for minimizing latency, they do this in VR too. Like for minimizing input latency, what they'll do is they'll produce a frame and then they will reproject that frame given new camera inputs. So they'll have like, you render a frame and you have all this depth information and all this stuff from producing the rendered frame. But by the time you're about to present the frame, the player's head will have moved in the headset, for example. And so that gives you new camera orientation information. And so what you can actually do is take the rendered frame, using the depth information, you can reproject it slightly. So you kind of do a mesh deformation of the frame, and you tweak it to be rendered from a new perspective, basically. There are artifacts, obviously, you don't have all the information needed to reconstruct the frame 100%, because obviously that would just be a new game tick. But this reprojection thing is actually pretty cheap, and so you can actually, if you produce a frame, you can reproject slightly given new camera orientation, which generally the artifacts are not noticeable because your head has only moved a very small amount, is the idea. So point being, that kind of minimizes input latency or perceived input latency. And point is, they were trying to do that same thing for Stadia. They were trying to use that technique to minimize latency. So I built this whole reprojection thing, and I don't think anybody used it, but it was pretty cool to work on, at least. And I built it, and it was actually Handmade Hero style. It was totally like I just kind of had free reign to do my own thing from scratch, and so I just built that. It was pretty amazing. So that was internship one. Then I did an internship at Insomniac, and then I did an internship at Apple. And kind of midway through my Apple internship, I was like thinking a lot about, I had done a bunch of 4-coder customization, so that's also wound up in the whole Handmade Hero story, because that's the editor that Alan built in response to Handmade Hero, and Casey ended up using it. And it was all customizable in C. And I would, so I built a bunch of customizations for 4-coder for myself, and which I still use to this day. And I was kind of thinking about this problem of sort of how difficult it is to do certain features in an editor that feel like they shouldn't be so difficult. So things that are very simple features from the perspective of the user, like go to definition, or if you type a function name and hit an open paren, like do you see a little tooltip showing you the arguments, or like if I rename a local variable, why is it such a hard problem for an editor to automatically rename all the usage sites of that variable? And so I was thinking about, like, I was kind of taking my game programming brain and applying it to this problem of editors. And I started thinking about, like, why is this not just a structured format? Like, why is code stored as text files? Why is it not that when I declare a variable, it's like as if I placed an entity in a level. And if anyone was pointing to that entity and I renamed the entity, nobody cares. They're pointing to it. They're not duplicating its name somewhere. So who cares? And so I started thinking in that direction, and I ended up starting just a personal project, which was a structured format editor, which it basically was like an abstract syntax tree editor. Turns out Alan was thinking about a lot of the same stuff. So I started this project. It was called Dion. Alan was doing his stuff, and he was super interested because I was posting videos about Dion, and he was like, that looks like a more fruitful direction than what I was coming up with. Do you want to work together on this? And so we worked together on that for a while. We made a prototype and ended up shelving the project, but the idea is not dead to me, although I'll say that. But point being, Alan, at that time, Alan was also at RAD working on the debugger. He got the job also from Casey, because he built 4Coder, and Casey was like, you should go work at RAD. So Alan went to work for RAD, and then because of our work together on Dion, Alan was like, Ryan would be a good UI programmer for the project, and so to build the front end for the debugger. And so he also recommended me to Jeff, and at that point I think I got another email from Jeff. And
I really want you to work.
Yes, and I'm like, man, like this is rough, because at that point I still had 1 semester left. I had 1 semester of school left. But I decided at that point, I'm like, I don't care, I'm doing it. I'm totally gonna take it. I did not drop out. I did finish, but I had like 3 classes left or something. And so I just did both. I just did both at the same time. Because I really didn't want to lose this chance. Because the debugger, telemetry is an amazing project, but it's kind of like it's less greenfield than the debugger was at the time. So with telemetry, you're sort of working within an existing code base. Whereas building stuff from scratch my whole life, it's like I really want to work on, stuff from scratch per usual. So the debugger was like really exciting for me. And so yeah, I just did school at the same time as I started work. The very first video call I ever had with Jeff, he was like, I didn't really know if I was still being hired, because it's the process of being hired to RAD seems like it was always very like organic and very not like, it's not like you get an email from HR and like this kind of thing. It's nothing like that. Like a few months went by and I hadn't heard anything from Jeff, and I was like, do I still have a job, basically? And I had my first video call with him, and he was like, by the way, we're being bought by Epic. And I was like, oh, do I still have a job? And I did end up still having a job. It just was, it was slightly weird, because I think RAD was sold to Epic like the 1st of January in 2021, or maybe the 31st of December in 2020 or something like that. And I joined January 25th. So it was like, there was a few weeks of just like HR kind of going through the pipeline, and then I joined January 25th. So it was like immediately after they sold, I joined. And so I was never technically a RAD Game Tools employee, as it turns out. But I was sort of grandfathered into their like sub-organization, I guess I would say. And they still had the old office. So there was like 1 year of working at the RAD Game Tools office doing a RAD Game Tools project, not technically as a RAD Game Tools employee. It was very, very strange kind of middle period, but yeah, so that's everything. That's day one to 4 years ago at this point when I joined. So
yeah. And you worked since then. You worked on RAD Debugger, is that correct?
Yes. So that's the project I first worked on. So Alan was on the RAD Debugger first. he kind of, it was his project at the time. There's one other person who was on the project called Nikita Smith, and he's still there. He's working on the linker now, the RAD linker, and he works on sort of like kind of lower level adjacent problems to the debugger. So the debugger was kind of Alan's domain, and then Nick helped reverse engineer the PDB format and, you know, unwinding on x64. So a bunch of like low level problems involved in a debugger. Nick helped with all those things. Nick also, I'm pretty sure, got the job through Casey because he built. Casey's just like, you know, the recruitment team for RAD, I guess. But Nick built a prototype, or not a prototype. It was like an alpha stage debugger for Windows, which was it was called CDBG, and Casey liked it enough that he recommended him to Jeff, and he's like, you should go work on the debugger. I think that was like, I remember this very distinctly because I really was excited about CDBG. This was pre-Remedy BG. This was all of that. It's like Visual Studio was what everyone was still using at the time. And CDBG came along, and I was like, wow, this is actually working. Like, this is amazing. And then Nikita posted a CDBG update, and he's like, I'm not going to be able to work on this anymore because I'm going to work on the RAD debugger. And I was like, God dang it. Like, I needed a new debugger because, again, this was pre-Remedy. So Nick, he's still there. He's working on the linker now. He's done a lot of work for, like, learning how to parse Dwarf, learning how to parse PDB, like all of those things. He's done a bunch of research work for the project over the years on that. And then Alan was kind of working on like the sort of debug engine side of the problem. And the initial plan was for me to come build the front end for the debug engine. It didn't exactly turn out that way. Like, there was so much surface area at the lower level parts of the problem, like actually parsing debug info from multiple formats, all of which have their own complications. Dwarf and PDB being like the main, those are the main ones that you're abstracting over. But there are other formats in the mix as well. So there's so much surface area there that I started helping out on the lower level parts at first. And eventually Alan left the project shortly after we kind of started the actual debugger. So we had built all this lower level tooling and you know, just we built this entire code base with all this code for debugger problems, stuff like debug info parsing, process control, things like that, operating system abstraction, obviously all the base layer stuff like allocators, strings. Like, we had this entire code base, and then we started the actual debugger, like the thing that's called raddbg.exe. That started, and then after that started, we Alan worked on the first iteration of the RAD debug info format. And then he ended up leaving, and then I was the only person on the debugger, and so I just kind of took over all of it. And so that's where we're at. So I think that we pushed our first alpha like publicly. It was not supposed to blow up in the way that it did, but it did. And we just tried to sneak it up there it was January of last year, so it's been about a year. And we just like silently put it up on the GitHub, and then people immediately found it. Like, within the day, people were like posting it everywhere, and it was like very alpha stage still. So I was like, oh man, like this is gonna be rough. It didn't end up being that bad, I think, but there were a few months where I was definitely like working weekends and kind of like trying to grapple with the overwhelming volume of people using it. But yeah, so that's where we're at. So that leads up to today, basically.
Okay, so before we dive into, let's say, the debugger technically, what is it, and like what does it need to work and function? Mm-hmm. Can you tell me what were the differences between your internships at Google, Apple, even Insomniac, compared to RAD/Epic Game Tools?
Yeah, that's a good question. So I would say that I had a very unique experience, I think, at Google, because I was kind of doing this internship project, which I had a lot of control over. I don't think I was supposed to have so much control over it, but my boss was very busy at the time. And so he was kind of like, this is your project, go for it. And he kind of just spun me up. And so that was actually a very RAD-like experience. Like, that that felt very much like how RAD ended up feeling to me. Because and given I think it was your conversation with Casey where Casey said that's kind of how he was with Jeff. Like Jeff was like, we need this in a year, do something, and off you go, basically. And like a very multi-threaded style of organization, I guess.
I would say like passing responsibility to employees, right? In a good way, like sharing it. Yeah.
Yeah, definitely. And so that's kind of what my first internship was, but I think it's a very, very unique situation, especially for Google. But Google is also very, they have so many different organizations that are sort of all, not all centrally coupled. So you can probably find experiences like that in various parts of Google. But Insomniac was very different because I was working on a specific engine. Like they had their entire engine code base. I helped out with like there was like a variety of things I worked on, and then I did a like a month and a half long internship project like towards the end of the internship, which was trying to hook up all their engine systems to like a ground truth based renderer for like, so you'd have this like slow ray tracing renderer which would do like ground truth based lighting and everything. So it's doing super slow ray tracing paths for lighting, for reference images for lighting artists to look at. So a lighting artist could say, okay, I've organized this scene and I want to see what this scene would look like if you just actually simulated the full ray trace, get an image that depicts that, and then they can adjust their lighting as they see fit, basically. But beyond that, I just did a bunch of smaller things, helped with some rendering performance stuff. I worked, I guess, most closely with the Stormland game, because this internship was in North Carolina. That part of Insomniac was responsible for the Stormland game which was a VR game that they shipped. And but I did some more general purpose like engine stuff as well. So like shockingly, I'll see my name in credits for like the Spider-Man 2 or whatever that came out, and I was like, I didn't really work on that game, so I don't know how I feel about that. But you know, you might find like a handful of lines of code that were written by me there, but it's not very definitely not like, it feels so wrong for my name to be in the credits because I just didn't work. You know, when you're so used to building the whole thing from scratch, it feels like you pour everything into it, and so it was very different at Insomniac because you're just kind of poking into an existing code base. Like it felt like what people kind of do with Unreal Engine, as well, because it's a very established code base, and that's just how that kind of situation was. So, and Apple was somewhat, I guess, like half of it was partly similar to the Insomniac experience in that I worked for the user space, basically the user space driver, like front end driver part of the Metal, like all of the Metal GPU software stuff. I worked on the user side driver for that. So basically, when you call the Metal function, like what are you calling into and what is it doing? And that was very similar, I would say, to the Insomniac thing, because you're working in a widely established code base. People are calling this code, it's doing real stuff, it's not greenfield at all. And then the second half of my internship was basically doing porting, like people might remember the Quake 2 ray trace thing. It was basically trying to use some new ray tracing stuff that they were doing with Metal and trying to port the renderer from Quake 2 RTX, trying to port that renderer to the Metal ray tracing stuff. And I made like a fair amount of progress. It definitely didn't look as good. I was kind of, I was somewhat demoralized at that point. I mean, this was during 2020 for context, so it was very like dark time, and I was just kind of demoralized. But I did make some progress on that front. But it wasn't the shiny demo that I had for my first internship for sure. But so yeah, that's kind of what my internships were like.
Okay, I have this feeling that you excel at the projects where you're given free reign and you're like, go figure it out. Like this is a complex problem. You need to analyze it. You'll need time to figure out what's the priorities, and then go there, work there. And in some of the internships, like at Apple, it was more like, here's the thing, can you fix that? And then here's another thing, right?
Yep.
And yeah, I think there's this like mindset. Some people would prefer one over the other, but I feel like when you said like you inherited everything that is now RAD Debugger and you like handle this, it's like it's such a different style of work compared to like task-driven work.
Right.
Okay, so back to the debugger then. You started working on this, and then at some point you inherited everything, and you did the shadow release, and it wasn't that shadowy. What kind of things debugger needs to function? Like, what is it comprised of, actually? Like, if you see a debugger, and by the way, why debugger standalone instead of debugger inside the editor? Like, what would be the advantages and disadvantages?
Yeah, so there's probably different ways you could define it. So I guess what I would start with is, for our debugger, it's a single executable. So the debugger is a program that you run, and it's an executable like a game. You double click it, it opens, and that's the debugger. There are other tools we package with the debugger for, because there's a lot of like adjacent problems to a debugger. Like a debugger has to be able to parse debug info. Turns out parsing debug info is very useful for other things, and so if you spend all of that tech on just one debugger executable, it's kind of a shame. So we tried to do our due diligence, and we have a bunch of other utilities that we package with the debugger, but all of them are standalone. So the debugger itself is just an executable. What is the executable and what does it do? Well, we can start with like the basic definition of a program as it's running, which is when you double click an executable, there's something that's spawned on, like the kernel will spawn something known as a process. And a process, it bundles a few different concepts together. I don't know how deep you want me to go, but each process gets like, things like a virtual address space. It gets several modules which are loaded, which modules, of course, are the loaded equivalent of like an executable file or a DLL file, or on Linux it'd be a .so or a shared object file, or an ELF like executable file. So these are kind of like in Windows terminology primarily, although you can map it to Linux as well. These are called modules. And you also have a set of threads per process. And so that's like let's say you're debugging a game. If you double click your game executable, that's like what gets spawned. It's like, okay, there's a process, you have an address space, you have modules and threads that are created, and that's your game executable. The debugger is another one of those. So a debugger, you double click it, it's a process. And the difference between a debugger and a normal program is that the debugger will talk to the operating system and say, I would like to register as the debugger for this other program. So I would like to attach to this program is how the terminology works. And what that basically means is that the debugger the kernel will store some state per process that's like, okay, this process over here, the thing that's currently attached to it as a debugger is this other process over here. And what that means is that the debugger will now be informed of all of the debug events that are generated by the execution of that other program. So if, for example, that other program, if it were to throw like a low-level exception, like it tries to access a null pointer, for example, anytime you try to access an address, there will be a page fault interrupt. If it can't not map to a physical address, the kernel will intercept that and say, okay, page fault, is this a valid address? Has it been actually reserved in their address space? Like, can we page something in to serve this request, or is it illegal? And if it's an illegal access violation, that's when like an actual exception will be generated. And if a debugger is attached, then the debugger will actually receive the control flow and say, the debugger is sitting there waiting for debug events, basically. The kernel will say, okay, here's a debug event, debugger. This thread tried to access this address, and this thread at this instruction address tried to access this memory address, and that's illegal, so you're the first one to hear about it. And while the debugger has received that event and is processing it, this other process is completely suspended, so it will not be executing. The debugger can do whatever it wants with that information. It could like snap to a line of source code. The source code UI could like draw an arrow that's like showing where that thread was or whatever. So that's like the general structure. You have a debugger process, you have your target process, and the debugger can attach to that target process. And all it's doing is receiving debug information, or I shouldn't say debug information because that's a separate concept, but it's receiving debug events, it's receiving information about what's going on in the process, basically. So anytime a thread is spawned, the debugger knows. Anytime a module's loaded, the debugger knows. If a process is spawned by another process, the debugger will find out about it. I should say the debugger can find out about it. Things like this. Now, the debugger also has the ability to read and write memory and read and write registers. So what this allows you to do, for example, is if a thread is stopped at some line of source code, you could, for example, before you resume the process, you could do something like place a bunch of interruption instructions. So int3 instructions on x86. They're a 1-byte instruction which cause basically any thread that hits that instruction will be interrupted and control flow will be transferred to the debugger. So the debugger will get another kind of debug event, not like a memory access violation, but it'll say a trap was hit, and the debugger will learn about it that way. And so what you can do as the debugger, you can use that to implement things like line stepping. So you can say like, I would like to step, if you have some idea of like this range of instructions corresponds to this one line of source code, and you're stopped at that line of source code, you could say, okay, I want to step over this line of source code and just like let all that code run, but then stop immediately after that line of source code has been completed. So what you could do is place a trap, which an int3 instruction, at the first byte of the first instruction after the line is after the range of instructions corresponding with the line, you place an int3 after that, and then you resume and then wait for the thread to hit that trap, and then it's like, okay, I've done a step basically. So you can start building these constructs and using these kinds of features, and you can implement things like line stepping, step over a function, step into a function, step out of a function, breakpoints where you put a breakpoint like a little red circle on some line of source code and hit F5 and run to it. And then you can also evaluate things like memory in a debugger, because again, the debugger can read memory. So you can evaluate things using debug information, which is basically how it basically records records a lot of stuff. There's a ton of stuff wrapped up in debug info, but one of the things that debug info will store is this correlation between instruction addresses and line info, and source lines, and that's called line info. So it'll basically say, okay, this range of addresses in this module is going to correspond to this file name and line number, basically. And so it'll store mappings and data structures which basically encode things like that. It'll also encode things like, if you're within this range of instructions, you are within this scope, and this scope has these local variables, and these local variables can be evaluated using that can get arbitrarily complicated, but with simple debug build type things, it'll usually be something like, oh, the address of this structure is the RSP register plus some offset, and then that location on the stack basically will be the base address. Well, that location on the address on the stack will encode that'll be like where a pointer is. Well, I mean, it depends. This gets into location information. So basically it'll say like, okay, this structure, the address is encoded at this location in the stack, or this structure is on the stack itself, just at this base address. Like, it can start encoding things like that, or it can say something like, okay, in this scope, here's a local variable. This local variable is stored inside of the RAX register, for example. And so the debugger can use that to implement things like, okay, I'm stopped at some line of source code. I'd like to evaluate this local variable. And you could put that into like the watch window, and the debugger has all the information it needs to actually evaluate that and display the value. So I don't know which parts of that you want me to dig more into. That's maybe a decent sort of overarching structure
That's a great overview because like
Okay.
in the beginning I thought the events are being emitted pretty much like every line is being executed, but this would be more in the like interpreted world, but not in the compiled world
Right.
necessarily. But so what you say is like the debug events are being emitted. If you are attached as a process, you can receive them. So if you toggle the breakpoints, you can insert the interrupt instructions, stop there, and then all of the evaluations and like ability to evaluate an arbitrary expression, see the call stack, everything actually needs to be kind of re-implemented on the debugger side using the information it received from the process.
Yes. Yep.
Okay.
Exactly.
Okay. I kind of thought that it's already there and the debugger will just display it, but there's a lot of work that needs to
Yes.
happen to actually have that.
Yes.
Okay.
Yeah, there's a
Okay.
remarkable amount of surface area to debugger. Yeah. Yeah, it's a
W-
lot.
w- how does it work then in the multi-threaded applications?
So in multi-threaded applications, it's kind of the same thing. So you're attached to, well, it depends on what how exactly the kernel organizes these, like this concept of attaching and stuff like that. It varies a little bit. So like the lowest level API that people use for process control on Linux, for example, is thread granularity. So you can have one thread attached to another thread. And if you're trying to debug a multi-threaded application, then you just have to have you have to attach to all of the threads basically within one process. In Windows, the debug API is process granularity. So you have a debugger process. It attaches to some other process. Target process can have several threads, and if any of them generate an exception, or memory access violation, hit a trap, whatever, the debugger will know about it, and when the debugger finds out about it, all of the threads in the attached process will halt. And you can also do multi-process debugging too. So you can attach to multiple processes at the same time. On Windows in particular, if any of the threads in a process, so like I said, if any thread causes an exception, all of them will be suspended when Windows reports the debug event to you.
Okay.
That's not true at the process granularity level. So you could actually, I tested this out at some point. If you attach to multiple processes, one of the processes generates a debug event, the other one will keep running, which I find very confusing behavior. So because then it's like, okay, the debugger is not just in a running or pause state anymore. It's also like a per process running or pause state. Is it very, very like that would have been a very confusing design. So in the case of the RAD debugger, we just hand suspend things ourselves. So if we ever see a debug event, all the processes that we're attached to will be suspended. But that's basically how that'll work. So yeah.
Okay. What is then debug info?
Okay, so debug info is basically like, so in order to cover debug info, maybe it's best first to walk through like the general structure of a compiler and a linker. So I'm sure anyone who's doing programming in a compiled language like knows to some degree what a compiler does. It's like you type in text, you hit the green arrow, and then you get an executable. That's incorrect in some ways, but it's like that's like day one when you first start programming. You're like, I hit the green arrow, that calls the compiler, and I get a little program that I can run or whatever. And that's a good like starting point. So in order to think about what a compiler does, you have to start breaking that down a little bit. So you can start thinking of a compiler as being, it's the Mike Acton thing again. It's a data transformer. The thing on the left side of the arrow, so the input to the function, is the textual source code that you put in, and the thing on the right hand side of the arrow is I'll fudge this a little bit and say, okay, the compiler and linker are in the middle. That's the name of this big function that we're drawing this arrow for. On the left hand side of this arrow is flowing from left to right. And on the left-hand side of this arrow, you've got your textual source code, your .c file, your .cpp file, whatever. And on the right side, you have .exe, like you've got your .executable or .dll or whatever you're doing. Now, if you break that down a little bit, first we can split apart the compiler and linker. We can say the compiler is not generating an executable; it's generating .obj files basically, or it's generating like object files. So it takes in the textual source code. It says I'm doing one translation unit. And so I'll turn all of this textual source code into machine instructions plus metadata and all this other stuff. And then a linker is taking a set of object files and producing the executable. So if we dig into the compiler part a little bit more, we can see that, how in the world do you turn textual source code into machine code instructions? And it's like, well, then you can start learning about things like, okay, you've got a parser, and the parser will parse the source code. You produce an abstract syntax tree. Maybe you do type checking on that abstract syntax tree. You produce a type checked abstract syntax tree. The type checked abstract syntax tree can be used to produce intermediate representation structures. Maybe there's an IR tree in there. Maybe it's a flat IR stream. Eventually you get down to some intermediate representation stream. Eventually you could generate down to native code like x86, like machine code. And so when you walk through all those stages, what's interesting is each stage has a backwards mapping to the previous stage. So you could imagine, and this is exactly in machine code, that machine code encodes assembly what you can think of as assembly instructions. And so this machine code has a bunch of instructions, and those instructions are they were caused to be generated by some line of source code in the input of the compiler. So the compiler's you have int x equals 0, x plus equals 1, or whatever. Those two lines of source code will be that will be in some ways responsible for generating a certain number of instructions. Okay, move 0 into these 4 bytes on the stack, or into this lower 4 bytes of this register or whatever, and then increment this register or something like that, and then move the value back to the memory location if it was in one, or whatever. Some number of instructions are going to be generated for those two lines of source code. And debug info is the recording of all those correlations. So debug info is going to say, okay, this range of instructions, we're going to back correlate that to this line of source code. Similarly, this range of instructions, we can also correlate it to information about what procedure this came from. So it kind of points backwards at higher level structures in the language. So it takes all the low level stuff, machine code instructions and what certain ranges in those machine code instructions, and it correlates those with higher level structures from the language. And what this does is it lets you build the user interface for a debugger such that you see these correlations at all times. So when most people use debuggers, they're not usually looking at disassembly. They're looking at their source code, and they're thinking in terms of okay, I'm going to step over this line, I'm going to run to this line, I'm going to put in this local variable or this global variable, and I'm going to evaluate these things. What's my call stack? How many layers deep in my call stack am I? I'm in the entry point that called into my game update thing, and I'm called into the entity, whatever, do stuff, or, whatever. That's the level that people are thinking at, and debug info is the thing that serves all of those purposes. It's saying, okay, at the low level, you've got this thread, it stopped at this address, and you have these modules loaded. What that lets the debugger do is say, okay, we'll take that address from the thread, map it to some module, map that module to debug info, look up into the debug info this relative address to the base address of the module, and then you can find, okay, given this address of the thread, we can now use these lookup structures in the debug info to correlate back to the language information. So we can say, we have this address, so we can start from the beginning. We have some thread, we map that to some virtual address, we map that to some module. The base address of the module lets us map that address to a virtual offset. That virtual offset, we also map the module to debug info. We take the virtual offset plus the debug info, and we can use that to map to a certain source file line combo, some path to some source code file and some line number. We can also map to some scope tree data structure that refers to some procedure. For example, there could be symbol information inside the debug info that's there's a procedure named foo, and it has this type, and it has this is its root scope, basically, and here are its parameters, and all of that stuff. Debug info is the thing that lets you take all the low level stuff, map it all to procedure, symbol information. When I say symbol, this was confusing to me early on. Symbol just means you can think of it as just a name that refers to some procedure or global variable inside of debug info, basically. Some people use it to refer to types as well. I'm not sure how I feel about that. Symbol is kind of an overloaded term, but Point being, debug info stores things about like, okay, types, procedures, global variables, all these things, local variables. It refers to all of those things, and it is organized so that you can take low-level stuff and correlate it to all those higher-level structures. Does that make any sense? There's a lot of stuff to cover, so it's...
Yes.
I hope that helps, yeah.
I'm trying, like 80% of my brain is trying to understand that, and 20% is asking myself, how can you be 1 year younger than me and know all this stuff already? When I'm like, I'm not even in the like first 10%. That's so impressive.
Working on a debugger really helps. Like, if you haven't worked on a debugger before, I wouldn't have known this if I'd never worked on a debugger. Like, I used debuggers before I worked on a debugger, but I certainly would not have understood like all of this minutia basically. But yeah, there's a lot of information in there, and it's so useful not just because it makes debuggers more useful, like because you understand more what they're doing. It's also that like, once you know what debug info contains, you can start just doing a lot with it. Like, you have a file that comes out every time you build that tells you every function in your program, where they are in the source code, all of the types in your program. Like, you have so much information about what your code actually is doing and what it's generating that it's I mean, it's awesome to have that information there. I mean, it's unfortunate that it's stored in like the PDB format, which is very complicated to parse and use, which that's why we have our own debug info format for the RAD debugger, which we produce by converting the PDB file, basically. So we take the PDB file, which is complicated proprietary Microsoft format, and we have a bunch of they've opened it more and more over the years, but when the debugger work started, it was not as opened as it was. So a bunch of reverse engineering work had to be done by Nikita Smith did a bunch of that, and maybe all of it. I don't know to what degree other people helped, but he did a bunch of that. And so we instead of working with PDB as our base like debug info format, we're like, let's just have a simpler format. Let's just do this most straightforward version of a debug info format that you could do, and then we'll just straight up convert the PDB. We'll just parse the PDB and output our own format, and then build the debugger on our format instead. And now with Nick's linker, you can also generate our debug info format natively from the object file. So going back to that compiler linker arrow thing, it's like the compiler does not produce executables, it produces object files. Those object files contain debug info as well. So the compiler basically produces, it compiles all these things to machine code instructions. It has a bunch of things like, okay, we're relying on these imports that we expect other object files to provide. So the linker has to link up those function calls or whatever. But it also generates a bunch of debug info. Now that debug info is not stored in PDBs. It's stored in sort of what PDBs contain, which is it's called code view, which is just the name of the format for like a bunch of the debug info that's stored inside of these object files. And so inside of these object files, you have like fragments of the whole thing that ends up in a PDB basically. So we can't control the compiler, so we still have to deal with code view, but now Nick's linker can actually preemptively convert that code view to our debug info format and export our own. Instead of exporting a PDB, it can export what we call RDI, which is just RAD Debug Info. So it can export an RDI file, which is like enormously simpler than a PDB. When I say that, I'm not trying to boast about it, because it's just like it's just so much more straightforward. Like, it's not that we did a really amazing job, although I think we did a good job on it. It's that it's just that PDB is just so darn complicated, and so it's hard for anyone to really use, and so it's just been a big headache. So yeah, that's why we have our own debug info. But
and PDB is Microsoft format, but also it's tied to the C++ toolchain, right? So if you're for example playing with other language, Odin, Zig, whatever, they won't necessarily use PDB, right? They might have their own stuff.
So no, they will also. So Odin, for example, like PDB files store debug info. Debug info is not really correlated directly to language constructs. There are things that are to some degree language specific, like type info type info will store things. Of course, this all evolved in a C and C++ world, and so there are things which are C and C++ isms. And for example, like if you're in a language like Odin, which has slice types, or any language which has a way to delimit the length of a pointer, basically, the debug info will not know about that, like, formally, if that makes sense. Because there's only a concept of a pointer, there's no concept of a fat pointer with a length stored next to it or something like that. So the debug info will not know certain things that have arisen in new languages, but the debug info does not have type information or symbol information or line information for that matter, that's specific to C and C++. It'd be wrong to say that they're not language specific, although it's just not the programming language that matters. It's actually the reason why a PDB file can be generated for Odin or JAI or whatever is because they're all using the same underlying language, which is text files and executables, and because they're working at that lower level and they haven't disagreed with that part, then they can hook into the same toolchain. That's kind of what debug info stores. So it's not language specific. There are language specific parts of a debugger, but debug info mostly keeps working because everyone uses text files. Line info is just a correlation of machine code instructions to text files, or to ranges of text files, basically. So that mapping keeps working as long as you're in a textual language, which if you're using Odin or whatever, you are. And so Odin does generate PDBs, JAI does generate PDBs, and this is all because LLVM generates PDBs. Like, everyone kind of is, on Windows at least, is generating PDBs. On Linux and stuff, it's using Dwarf, which is the Linux ecosystem debug info format. But so yeah, it's not really language specific. So the format does work more broadly.
Okay. Who is now using RAD Debugger that you know of?
So, I think Jeff is using it pretty regularly now. Casey, I believe, is using it now. I use it now. And
you hesitated.
Yeah. Well, I do actually use it. Sometimes it can be kind of a mind bender. If I'm working on the debugger, I have to debug the debugger with my debugger, and that can get kind of unstable. Like, if I'm debugging a really bad bug where it's like the debugger is unusable or something, I could have a stable version that I'm debugging. I hate thinking about that kind of thing, though. It's like, okay, I'm debugging the unstable version with my stable version. At some point, I really just should start doing that. For a long time, obviously, you either have to bootstrap yourself by not using a debugger, or you have to use somebody else's debugger. So I used Remedy before the RAD debugger, and so I used that for our debugger for a while. Although now it's getting stable enough to the point where I can debug itself with itself. So, so I use it, Jeff uses it, Casey uses it. There's a bunch of people around who seem to be using it, like I'll see people randomly on YouTube using it. There's people, I don't know. So I think some small number of people are using it at Epic. So it's not quite the big reason why like Epic would care about a debugger, for example, is because it's really important to have a debugger for engine programmers who are working on something like Unreal Engine. Unreal Engine is very large, very complicated, and it's like it has a bunch of modern C++ stuff in it too. And there are a few things that are going to be missing for people who are in that kind of a code base in the debugger currently. So it's not like been widely adopted at Epic yet. But I think there are a few people playing around with it. There's one person I know who works, I think, on MSVC, at Microsoft on the compiler. I think he's using the debugger. So it's getting around. I don't know who's using it and who's not, to be honest, because there's no like telemetry or anything. But people do seem to be using it to some degree.
This ties into my next question. RAD was licensing, for example, Bing, Codec, and they were selling software, right? And RAD Debugger is open and developed openly now. So what changed there, and what was the rationale? And like, provided that you can speak about it.
Yeah, I think it's fine for me to say. It's like, what changed there? I mean, it could probably be summed up in one word, which is Fortnite. But
Okay.
I think really like to unpack that a little bit. I think it's basically like the debugger. There's a lot of benefits to a debugger project being open, especially certain parts of it being open. Like it's very useful if the debug info format is open and all the tooling for the debug info format, because formats, closed proprietary formats, like everyone hates those, rightfully so. And so there are already things part of it that should be open sourced. The rationale to open source the rest of it is like general stability. Like people who are using the debugger, if the debugger's failing in some way, because they're in new, unique circumstances that we haven't tested with, they have a much greater degree of understanding what the problem is and what's going wrong, and reporting that to us than if it were completely closed. It's not that you couldn't do that if it were closed, but it's just more useful to programmers who are using it to understand what's going wrong and reporting issues that way. And that's, in practice, that's worked pretty well because like people have all the source code to the debugger. It's really easy to build, and so if the debugger fails, they can very easily attach to the debugger with a different debugger and say like, oh, it crashed right here. It's trying to access this pointer. That's a bad pointer or whatever. Like they can start looking into that immediately. So that's just more useful for them, and it's more useful for us for general stability purposes. So there are some things like that. I think that there's another aspect, which is that if you're going to open source part of a project, it gets kind of annoying to open source part of it and not open source all of it, because you have like weird bifurcations in your code base. It's like, am I in the open source part? Am I not in the open source part? Like, what is going on? And the other thing is like, would it make significant enough money for Epic to care, versus if the debugger was just good, if it were a good tool for people at Epic, would it make them more efficient? And would that actually would any money that they made from the sale of the debugger add up to anything approximating how much more efficient people would be? Because they're not like waiting on Visual Studio to take 2 minutes to load their program and then fail or something like that. So I think that the rationale is basically, it's a tiny crumb on the plate of Epic, where the main course is like Fortnite or whatever, and or like it would be a tiny crumb probably even with respect to like Unreal Engine sales or something like that. And so it's like they make almost nothing. There are some benefits to be made from open sourcing it. It'd be a good thing to open source it as well, like just altruistically. And so I think that's kind of the direction that I think that's why it moved that direction. Jeff had told me at some point, he said, if this were RAD, we would sell it, because that's how RAD made its money, by selling software. But Epic does not make their money that way. So, in fact, Epic does a lot of free stuff, actually. So, just when you change the business model, it's just changed, kind of changed the meta structure that the debugger project was in. So, yeah, I mean, I'm really happy about it, because now, like, all of my hard work does not have to be locked behind a wall forever. You know what I mean? So, so I think it's a really good thing.
It's a standalone debugger, and to be honest, I never used a standalone one. I always used the IDE one, even though I never really worked in Visual Studio, more on the JetBrains IDEs, so like their versions of the debuggers, and I never like paid a lot of attention to debugger as a separate thing. So what would you say like to people like me that like when would I open up a new window when I have, for example, something that is integrated into IDE? How does this work?
So the rationale for a debugger to be separate from an editor, I would say, the first thing I would say is that the functionality needed to implement a debugger is probably more different from that needed to implement an editor than people might think. So I think in order to kind of express this at a high level, what I would say is that it's worth understanding that the inputs to what a debugger is doing, the inputs are different than what an editor is doing. And to express that, I'll just like sum it up by saying the debugger is working with an executable which has been built and source code which has been used to build that executable. And so it's working with source code and all of the things you get from applying a function to that source code, which is like the compiler and linker. And so it's really interacting with source code in a very read-only kind of way. So you have debug info, which tells you all this information about how your executable correlates to the source code. An editor's whole purpose is to modify the source code. And if you're modifying the source code, you're now invalidating the debug info. And so a lot of people might think that there's more code there shared than there actually would be. Like some things in the UI, it's like, sure, you have a source widget, you have these common UI paths which maybe look very similar. If you put a picture of a debugger next to a picture of an editor, some people might say they're the same kind of program. But really, there's not a lot of overlap beyond like very high level stuff, and it's because it's not, like I said, it's not so much about the UI part. It's about everything kind of surrounding and facilitating the UI. So, for instance, syntax highlighting in a debugger is very, very different from syntax highlighting in an editor, because an editor has to deal with invalid states of text like all the time. Like you type the name of a new function you're creating, you have open paren, close paren, and then open curly brace. Instantaneously, the language will see that as invalid. You haven't typed the body of the function yet. Every character press you have is like going to be an invalid state for the language, like almost every single one. And so not every single, you hit new line, you're still safe, there are things that are still safe, but it's like, you can't take a general language parser, and I mean, people do this with language server protocols, but I think it's still not quite the same thing. Point being, an editor's working with like read-write text, a debugger's working with read-only text, and all of the information that the compiler and linker produce from analyzing all of that text. And so syntax highlighting, go to definition, highlighting the names of types, things like this, they're all different between an editor and a debugger. Like a debugger can just say, okay, I have this identifier that I'm going to render on the screen, look it up in the debug info, is it there? Great, I know it's a function, color it that way. An editor has to be managing its own code index of things. It has to be like always incrementally parsing your text in one way or another, and building its own index, which is continuously being rewritten. So the first thing I would say is like, the problems are not as similar as people might think. But that being said, I understand the desire for integration between an editor and a debugger. Like I don't say that meaning to say, oh, it's totally fine that these things are completely separate and, who cares, basically. I would just start by saying, like, that's the reason why there's a different program at all. Like, that's why they're not the same program, because they're actually very different problems. So the next thing I would say is that because they're different problems, the UIs also tend to be very different. So in a debugger, you do have a source view, like you do view source code. You also view a lot of things that you would never be thinking about in your editor. So while you're editing source code, you're never going to be thinking about the disassembly that you got from the last time you built your code, really. In a really cool futuristic editor, you might be wanting to see like Godbolt style stuff, like as you write code. Like that'd be great. So maybe disassembly, maybe some version of that you'd still definitely want, but you probably wouldn't want things like a watch window or a call stack view. Like these things start making less and less sense. A breakpoints view, well, if you're placing breakpoints in your editor, maybe I could see that, but some of these start making less and less sense. Like for example, in the RAD Debugger, we have the scheduler tab, which is used to just show the process, like all the processes you're attached to and all the threads you're attached to. And then you could freeze threads and stuff like that. That makes no sense when you're editing source code, because you're not running a program. Like, it's so a debugger spends a lot of screen real estate and a lot of UI real estate on things that are completely irrelevant to an editor. And the same thing happens with control schemes too. So in old debuggers, as I understand, like the control for stepping over a line of source code was S. You just hit S and it steps over. Nowadays, because of Visual Studio, which does this winding together of the editor and debugger, everyone expects it to be like F10 or F11. But, because if you're in an editor and you hit S, it's like, what happens? It's like, oh yeah, it writes an S character. But in a debugger, like when you're debugging, you're not trying to modify the source code, really. So it's kind of like coupling these things together. I understand why people want it. It kind of makes sense in sort of a modal form. Like I could imagine switching between editing and debugging modes, like in the same program, which Visual Studio kind of does that. It also kind of doesn't. So it's, I don't know, Visual Studio is not maybe a good model for what you'd want, so yeah, that's the next thing. The core code is different. The UI is different. The problems are different. Do I think that there should be tighter integration between editor and debugger? Yes. And unfortunately, I think that with the way programs on an operating system today interact, it's usually a little bit less powerful than I think people want. Because there are ways to special case the integration between a standalone debugger and a standalone editor. And people do this all the time. So including with the RAD debugger, like you can set it up so that when you navigate to some spot in your editor, it'll navigate to the same spot in the debugger. So you can do things like this. You could say from your editor, the editor could run a command that causes the debugger to launch and run and stop at some line. So you could say run to this line and then stop there and then go to the debugger then. You can do these kinds of integrations with an editor. And you can kind of special case it. I think what people would want more than that, though, because special casing it is kind of annoying. You have to do it for every single possible editor. You have to, it's not great. So people want the more integrated thing because it's just taking care of that problem for them. In an ideal world, what I would hope for is kind of richer integration tools at the operating system level to facilitate communication between programs in a little bit more seamless of a way. So the ways that programs can communicate today are very manual and user-driven, in that programs either have to be written specifically to communicate with each other through inter-process communication, or some mechanism of inter-process communication, or all of the stuff the user can do is like completely manual. It's like, oh, copy and paste this string. Like I have this path open in my editor, copy that path, paste it into the debugger, go to this line, like you. Or save a file on disk and then open it in the debugger. It's all very manual. I think you'd want richer operating system primitives to actually facilitate like more seamless integration between tools. But that's a separate tangent. That's my toy project idea that I'm kicking around in my free time. But okay. But so we don't have to go down that rabbit hole. But point being, okay, so. Maybe that's I've gone over 3 points. This might be a little disorganized of a way to dig into this question, but I think the last thing I would say, this is another UI point. I would say that you could imagine having a debugger serve as sort of a like the debugger adapter protocol does this, for example. So there's something called the debugger adapter protocol where you can have some debugger. It hooks into editor front ends, and so the editor provides all the UI for things like stepping, watch window, whatever. And the debugger just facilitates that kind of stuff. And the reason why that falls short is because a really good debugger needs to do a bunch of UI stuff that it completely controls that editors cannot possibly predict. And in fact, that they haven't predicted. If the editors actually did predict this, then maybe it would be okay to use something like a protocol like that. But so far, they've been built for very old models of debuggers that don't support a bunch of the stuff that, for example, we want to do in the RAD debugger. So general purpose data visualization, where you can say okay, grab this pointer, evaluate it in the watch window. I want to view this as a bitmap, or I want to view it as some geometry, or I want to view it as a sub hex editor view just for this one pointer. You can do all that stuff in the debugger. None of those UI paths, to my knowledge, would really be well supported through something like a debugger adapter protocol. So because of the limitations of that, it's to me at least, it seems like the best relationship with a standalone debugger to an editor for people who want a tight integration between them would be providing all the mechanisms so that the debugger can be driven externally by some other program, and providing mechanisms for the editors to receive information from the debugger, like where are breakpoints set, stuff like this. And then I think just letting people special case it, unfortunately. So I don't know. Hopefully that's a sufficient answer. It's the reason why you'd want it is because you can do much richer stuff in the debugger if the debugger controls its UI. But that doesn't disqualify tighter integration.
Okay.
You do have to Alt Tab, but it's like, I don't know. What do you want?
It's not that bad.
Yeah. Yeah.
Can you tell me at what stage of your programming you decide you need the debugger? Like, you need to use the debugger. Like, because it's not like any kind of error, right? You're gonna probably like mess around until you realize that you don't know what you don't know, and you need to really use the debugger. So like, what is the point? At what point you're doing this?
So, do you mean like in my programming history when I started using a debugger, or do you mean in my day-to-day programming work?
Yeah.
Oh,
The latter, yeah.
okay, ladder. Okay. Basically, because I've become so comfortable with them, I will do it anytime I see a crash, anytime I see something unexpected happening, I will switch to the debugger immediately and just step through the code. And
Okay.
I do that because it's a much lower friction way of beginning to gain insight into a problem. So a lot of people bring up like printf debugging, stuff like that. I mean, I'll read the code first. Generally, what I'll do is I'll read the code. If I see the issue immediately, I'll be like, oh, there it is, done, fix it. If I'm not sure what's happening, then I will say like, the first thing I'll do is run it from the debugger. So I'll say like, okay, I hit a crash or something weird. Is there like some... Mostly this happens with crashes. So it's like, okay, the program crashed, what's happening there? Switch to the debugger, hit F5, and then like try to do the same thing. And then when I see the crash, the debugger will report like, oh, this thread was here trying to do this. This is what caused the program to crash, basically. So that's step one. If it's not a crash, or if I'm not sure why the crash happened, then what I can do is I can start saying like, okay, like unwind the stack a couple layers. Let's see who called into this, who called into that. Why are they passing this argument? I can start evaluating things. So I don't know. That's kind of what the workflow ends up looking like. If code is not behaving how I would expect it to, given my quick, brief read through of it, then I will step through the code in a debugger, and it pretty immediately clarifies like why code is not doing what I think it should be doing. So that's kind of what my workflow looks like. I guess I would say.
That's because I've realized maybe too late, but that there is like a whole type of programmers that don't use debuggers at all.
Yeah.
And they're like only print debugging.
Yeah.
And to me, that's wild.
Yeah.
I always want to have a setup where like if push comes to shove, I can enter the debugger and have everything immediately ready. What would you say to those programmers?
So I think that the first thing I would say is that it's a false dichotomy. Like, I use log debugging too. I would prefer instead. The first thing I would say is like print debugging already kind of shows how limited it is, because when you're talking about print debugging, you're thinking of textual logging. Like people are thinking printf, print out some text here, print out some text here, print out some values, whatever. The first thing I would say is like there's a better version of that, which is log debugging, where you can log arbitrary stuff and visualize it arbitrarily. The second thing I would say is like a debugger could visualize that stuff. Like it's not that if you use a debugger, you're never logging stuff. And it's not that if you are logging stuff, you can never use a debugger. You should use both for problems that kind of fit. Like logging is useful to gain certain kinds of insight into problems. Debuggers are also useful and much more efficient to gain insight into other kinds of problems. So, yeah, the first thing I would say is like don't pigeonhole yourself into one technique to try to suss out issues. Debuggers can be very, very efficient, much faster than log debugging for a large variety of purposes. The other thing I would say is like a debugger is not antithetical to logging. Like I told you earlier, a debugger is literally receiving a log of debug events. It is logging. It's doing all the same stuff. Now, there are some fundamental performance constraints depending on how kernels expose debugger functionality, depending on how this, depending on exactly the shape of the problem on whatever system, there are some constraints on what kinds of logging a debugger can can enable, and also how useful it is. So for example, if I'm doing like a whole giant batch processing kind of problem, like the PDB to RDI conversion problem is a lot like this. It's like you're parsing like potentially millions of procedure records out of a PDB file, and you're producing millions of new procedures in this new format. And if like one problem is specifically happening in some particular case and you're not exactly sure how you would break there in a debugger, it's like you might as well just log it and see and sort of and just like inspect the log after the fact. A debugger, the fundamental design of a debugger would not prevent logging from working that way. Like you could actually, without even having to modify the source code, you could say add a log point instead of a breakpoint, add a log point and say, okay, append this to the log, and this wouldn't even have to be textual information. It could be graphical, could be some arbitrary blob of bytes or whatever. You could say log this at this point in the program, and then after you run through that code, you just have this whole log of all this information. So a debugger could literally be facilitating this process. Now, like I said, there's some performance constraints. If we rewind a little bit back to how debuggers work, the way that a debugger can kind of interleave its code with some code that it's debugging, it can insert an int3 instruction, and that int3 instruction is hit by whatever process is running that code. What happens? Well, immediately the int3 it'll run the signal handler for this interrupt instruction. The kernel can say, oh, a debugger's attached. Okay, context switch to the debugger. Do not schedule this thread from the process anymore. Context switch to the debugger. Debug event. Debugger can do something. This is how conditional breakpoints work, for example. Debugger puts an int3 there. It has some condition, some condition it needs to evaluate. A thread will actually hit that int3. It'll get reported to the debugger. The debugger can evaluate the condition and say, should I stop? If no, if the condition evaluates to false, then just resume execution on the target and keep waiting for more debug events. Now, like I said, you have to context switch. Like the debuggee will have to will first like go into kernel mode. The kernel will see like, okay, there's a debugger here. Report this debug event to the debugger. Then the debugger has to be context switched in. And then if it resumes, then it has to context switch back to the debuggee. Like the debuggee has to be rescheduled and has to resume execution. That's a very expensive process. So if you do that in like a hot loop where you're iterating potentially like millions of times, it's just enormously slow. Now this doesn't have to be the architecture. In fact, on a different kind of operating system kernel, or with different features, like a slightly different, like just one feature that the Windows kernel could expose for debuggers, for example, which I'm not 100% sure on the exact shape of this, but if the kernel provided the ability for the debugger to say, so when you see an int3, before you go the full route of context switching all the way to the debugger, let me, the debugger, register this piece of code that I would like you to run in the context of that process. And that code could make the decision to either, yes, do the full context switch to the debugger, full round trip to the debugger, to send the debugger event all the way to the debugger process. Or it can make the decision to just continue there in the actual process. If you had that feature, conditional breakpoints would be like instantaneous. Not literally instantaneous, but they'd be near normal speeds of code. You could also do log points. You could do basically printf debugging, but you don't have to rebuild your program. You can just like stick stuff there and generate logs very rapidly, much more quickly than printf debugging. Unfortunately, on Windows, like I think there may be some mechanisms to do this kind of thing on Linux. There isn't really one on Windows, to my knowledge, without writing your own kernel driver. But then you have Then you have to ask people to like enter admin mode, install this kernel driver. It's like that's not really like workable. But so point being, sorry, that's like a major tangent. Point being, log debugging and like using a debugger are not a dichotomy. Use both. Use whatever works better, and get excited for debuggers to like have more logging features, because it's not that you do one or the other. It's that debuggers are they're hand designed to like make certain cases of gathering information about the execution of programs as fast and as much of a breeze as possible. And if you like say, oh, okay, I don't need that, I'll just printf every single time, it's like, I mean, that's your choice, but you're spending like 30 seconds to add a printf. You know, you have to go to your editor, find the right spot, add a printf, rebuild the program, go back, start the program, get to that same point, and like inspect the log afterwards, versus like running to that spot in the program and evaluating a variable immediately. Which, you know, you could imagine that taking a couple seconds if you put it in the watch window. But if you have, most debuggers have the ability to hover evaluate. You can hover your mouse over the variable name and see its value immediately. So I don't know. It's a lot faster in a lot of cases. So people don't pigeonhole yourself on stupid like internet tribal debates. Like just use debuggers when they're useful and use logs when they're useful.
With the idea of the debugger like visualizing things in a way that makes sense, for example, like even like vertex buffers or like things like that in a like render doc style thing, like this breaks my mind. Like this would be so cool to have a debugger. It's like,
yeah,
oh, what have I put into this buffer? It's like, oh, this. It's like,
yep.
Ooh, nice.
Yeah,
it's so cool.
Yeah, and you could imagine like with really solid log debugging too, like, and this would work even though I said there are performance constraints on it with the way debuggers are forced to sort of operate today. If you had, but even in that context, like for certain problems, it's still fast enough. And so like with conditional breakpoints. And so, you know, one thing a debugger could do, because it can evaluate memory across time. You could also imagine that like at every sample at some point in time, it could record the state of memory at that possible snapshot. Like at that point in time when the program was executing, this is what memory looked like. And so what you could literally do is add a log point and generate a log of basically all of the deltas to this memory across time. And if you visualize all of those as 3D geometry or a bitmap or whatever, you could like scrub through a movie of like all of the deltas to the memory that you see. So you could like, okay, when we start building this vertex buffer, there's nothing, and then you scrub a little bit further, and then you see all the vertices being placed, and currently, so I don't have in the RAD debugger, I don't have the log style thing. Like you can't scrub through it exactly currently. There's no log debugging stuff currently, although all of that is on the table for me. But you do have geometry visualization. So as you step, you can live update, see like your code changing memory as represented as like 3D geometry, or as bitmap data, for example. Like you see all this stuff just live as you step. It's a much tighter loop. If you imagine the fundamental flow of a computer being like human interacting on this side, computer there's output coming from the computer via the screen and the speakers, and then there's input coming from the programmer via the keyboard and the mouse or whatever. And the idea of a really good programming environment should be like that loop is as fast as possible. Like it's almost like the programmer needs to be sculpting the program. If you imagine that loop being as fast as possible, like that's really what a good debugger is facilitating. It's facilitating one part of that. So it's like you just get so much better. I mean, imagine having to like printf vertex data to a log, and then like, I don't know, would you have to put it out in OBJ format and then open it up in an OBJ viewer, or you know, what exactly are you going to be doing? Like it's just so much worse. Yeah.
Okay. What's on the roadmap for a debugger?
So the first thing, so very soon, I will be doing. There's a system in Visual Studio known as NatViz, and NatViz is a way of taking like very sophisticated data structures. Well, they don't have to be sophisticated data structures, but this is why people use them. It's very complicated, usually C++ crazy data structures where it's like if you ever, without NatViz, if you evaluated like an STD vector, for example, in a C++ program, you would like expand this, you'd expand it in the watch window. You're like, okay, put in this vector, expand, I want to see what's in this vector. And it's like, I don't know what it looks like on all toolchains, because obviously every toolchain has its own implementation of this. But on the MSVC toolchain, it's like, what is this type? Like, what exactly is in this class? Like, it's just complete, it seems like complete gibberish. And then if you actually, and STD vector is the sane one, like by comparison. It's literally a pointer and a size, like that's what you want to see. And then, you know, ideally the debugger would be able to suss out like, okay, the size is the size delimits the pointer. Like the pointer points to this many elements, depending on the size, rather than just one. Basically, like that's what you'd really want in a debugger. And I don't know, there's like so much nonsense when you look at just the raw view of an STD vector. So NatVis is the system for the debugger that's designed to basically like, I don't want to say clean that up. It's meant to allow people to ignore the problem. So the problem is that the data structures are complicated. Like that's the fundamental problem. It's like your STD vector implementation is just complete nuts. Like it's just complete insanity. But you want the debugger to be able to pretend as if it's not. And so that's what NatVis is for. And it's not 100% like that. Like I'm being a little bit facetious when I say that. It is a lot of that kind of thing. It's like, this wouldn't be a problem if your data structures were simple, but people don't make simple data structures. So they have these complicated structures and complicated data structures that they want the debugger to visualize in a more simple way. And NatVis is sort of the system for like describing how that happens. So instead of like just, you can imagine you put a struct in the watch window. What's the rule if you expand that struct? The default rule would be like, okay, iterate the members of the struct. Each one of those gets a row, like stuff like that. NatVis is just about tweaking that problem, basically, depending on type. With the RAD debugger, we have a whole visualization system for what I was talking about, like up to and including 3D geometry visualization, bitmap visualization, excuse me, all kinds of stuff like that. And basically I need to mature that system a little bit to kind of encapsulate more of the cases that people use NatVis for. And this is really so that it becomes more useful for people working on like Unreal Engine, for example. Like they need to be able to look at C++ data structures that are inside of the Unreal Engine and see them in a way that's useful to them in the debugger, stuff like that. So that's the next thing on the plate. And beyond that, it's like more performance improvements, more just better support for large C++ code bases like Unreal Engine. But once that's actually done, we're actually going to be pretty much going full steam ahead on the Linux port. So currently the debugger it's just a Windows x64, like that's where we started. But like long term, the vision of the debugger was always to be on Linux as well. And so we're actually not as far as people might think from that. So we're going to be doing that pretty soon after. In fact, in some ways we're already starting. So yeah, we'll have Linux support like hopefully sometime this year. I mean, people always ask me for dates, but insert XKCD comic about like software engineer predictions of when they'll finish stuff. But yeah, so we're going to be doing Linux port stuff. We'll probably do some other porting stuff to support probably ARM, and there's other various weird combinations, like if you have dwarf debug info on Windows, so you're not using PDBs, you're using MinGW or something, and or Clang, and you're outputting dwarf information for your Windows PE files, which is a very weird case, but it's like people do it. We'll probably want to support that case, then Linux with dwarf, and then probably some ARM stuff, possibly. And then after that, we'll probably go. I mean, there's tons of like crazy debugger ideas you can imagine. I mean, there's time travel debugging, so you could run backwards. So basically, that's a whole rabbit hole.
What?
Yeah. So like, if you basically like, let's say you're in some state of the program, you hit a breakpoint, and you are like curious about why. You're curious about what happened in the whole history of the program that caused like this particular thing to happen. So you're like, okay, I want to find out when someone wrote to this address last. You're stopped at some point in the program. You're like, when did someone write to this address? So okay. The mechanism for that, for people who don't know, is called a data breakpoint. So a data breakpoint basically is a CPU feature where you can set up the CPU registers to basically say, if you're trying to write to this address, raise an exception. Like basically interrupt the execution of the code, the debugger needs to know about this. That's a data breakpoint where you can say, for these 8 bytes at this address, if someone writes to this, I want to know about it. And so it's kind of like it's a little bit fancier than like an int3 instruction that you put into the source code. It's almost like you're putting an int3 at any place that would be writing to some address, if that makes any sense. So it's very useful for finding out, like, okay, like you're running your program, somebody screws up, tramples over some data structure, who's writing to it and why, should be read only or whatever. So you run the program with the data breakpoint on some address, and then you see who's writing to it, and then you can diagnose the problem from there. Time travel debugging, you can imagine running backwards. So you're stopped at some point in the program. You're in very non-deterministic code, so it could be very stateful. It could be very like hard to replay this particular thing. And so you could say, okay, I'm stopped here. I want a data breakpoint on this address, which has changed to something that busted. Run backwards, effectively, to the last time someone wrote to that. Now, it's a little bit misleading because that's actually what the UI flow feels like. Like, you do feel like you're stepping backwards and running backwards and stuff like that. What it actually is it's like a snapshot-based system. So basically you say, okay, there's some point where you start capturing, and then all these deltas accumulate and everything. And the problem of time travel debugging is basically saying, so if I step backwards, basically what you're doing is rerunning the same code as deterministically as possible, but then you just stop at one point before that. And so similarly, running backwards would be, you have this capture, you start from the beginning, data breakpoint at some address, and then you run until you hit it. It appears as though you ran backwards, but it's really like, the implementation is a little bit less magical sounding.
Would it be difficult to implement as like reverse instructions for each instruction?
So there's a lot of different trade-offs for stuff like that. It's I haven't implemented this, so I probably don't have a good full understanding of all the different trade-offs. It is pretty complicated though, because if you start doing stuff like that, you have to start emulating the actual instructions yourself, rather than letting the CPU just run them. So generally in a debugger, you're just like, okay, run this code, go. Now people do emulate CPUs and reverse them and do stuff like that, but it comes with some pretty bad trade-offs. So you generally don't want to do that. Also, I don't think you can do it without you still need the snapshot structure, because in order to, for example, replay a memory write, you have to know what was in memory first. So you need some kind of like history, keeping track of what changes were made and when. But yeah, I like I said, I haven't implemented that style of debugger feature yet, so I don't have a full understanding of all the trade-offs. The basic idea of the time travel debugger is like somewhat simple. Like, you have this snapshot, you accumulate which memory changes happened when. You only need to store the deltas, so it can be fairly well compressed. Well, actually, you don't even need to store the deltas. You store the initial state, and then the code is actually the delta. The code tells you how to change the initial state. In practice, it gets much more complicated because of determinism problems. Like, what happens if you write into the file system, you try to generate a random number from the kernel. Yeah. It's like you're doing very non-deterministic things. How do you keep all those things deterministic so that the snapshot even works? It's like, that's when it gets kind of hairy. And you can do it, but it's just complicated, and there's a lot of edge cases and stuff like that. So yeah.
Okay. Not this Linux port time travel debugging.
Right. So the other thing I was going to say, I don't know if that's going to be first priority. I think for me, the first priority would probably be, I don't know yet, because, we'll talk about it once we get to that point after the ports happen. But for me, I feel like one major priority would be just like really making the visualization system as good as possible. So one thing a lot of people want, Casey has talked a lot about this, is that custom visualizers for the watch window. So right now the watch window supports arbitrary visualizers, but it only supports arbitrary visualizers that the debugger currently defines. So it's all based on a hook system. So you could imagine plugging in your own visualizers into the debugger so that you could have your own custom visualizer visualizing stuff in whatever way you want in the watch window. And that's obviously, whether or not people would want to write plugins like that, it is kind of immaterial, because that's how the debugger visualizers should be written, like even the internal ones. So that's how it's architected. What Casey has spoken about before is it would be great if you could define a visualizer in the debuggy process. So in the debuggy, you have some function that you write that's like, here's the RAD DBG visualizer for this type or something. And then you write this, like, it's like a, your entity data structure or something, or your level data structure. And you visualize a grid of like, oh, here's where all the entities are, and so on. So whatever custom visualizer you want, or here's all the lighting data, here's all this gameplay stuff that we're debugging or something, you can just write the visualizer in line in your program, and then the debugger could call that to fill out its visualizer. So there's a lot of like cool visualization feature stuff you could do. So I feel like I would want to really make all that stuff really solid, make the memory viewer as good as possible, make all of those things really good, make them all integrate in a very clean way. So like if you hover a vertex in the mesh viewer, highlight the same bytes in the memory viewer. Like there's so much low-hanging fruit, so you can just get a much better understanding of what your data is, how code is changing it across time, and so on. And then yeah, that's probably what I would think is like very high. That would have a lot of returns, and it's pretty low-hanging fruit. And then yeah, there's like time travel debugging you could do log debugging like I was talking about earlier. You could do a lot of stuff like that. I'm not sure what's going to be the first priority after the Linux port, but it's going to be that direction of like futurist. Oh, maybe remote debugging will find its way in there somewhere. So your debugger client is on some machine. This actually might come before all this fancy stuff, because if you want to debug some game console running a program, the debugger has to talk to that somehow. So we'll probably do stuff like that, and then we'll go into the fancier direction of just like wild debugging features. But
okay,
yeah.
Okay. Well, what are the performance bottlenecks in debuggers in general? Like where do you need to spend time to optimize?
So I think that in terms of kind of depends on which part of the problem you're talking about. So basically one huge system in the debugger that's used all over the place is the evaluation system. And the evaluation system is basically it's basically like a little compiler. Like the entire purpose of the evaluation system is to take some expression that could be from a watch window, could be from source code, whatever, and parse it and generate some bytecode or something, or interpret it or whatever, and evaluate it and produce results for the user to view through the UI. That's like one very important part, and that shows up in many places. So if that's really, really slow, or not built to predict basically slowness, it could really destroy the performance and the experience of a debugger. There are other things as well, like there's so many UIs in the debugger. There's like it's potentially true that all of them could be bottlenecks if you really like did them in a certain way. So one thing that I've spent a lot of time being careful about, I wouldn't call it optimizing. I've just tried to do the problem in a relatively smart way, I guess. But for the watch window, for example, if you're in Visual Studio and you're in the watch window and you have an array, and this array is, let's say it's like 1 million elements large or something. You've got an array, it's got 1 million things in it. You want to open it up in the watch window and like scroll through and see the values or something. If you try to do that in Visual Studio, it will not work. It will like either crash or hang, or something bad will happen. So I've spent a lot of time trying to organize our watch window to be very smart about what memory it's reading, and basically like constraining the problem, because the reality is like the UI is not viewing an infinite number of things. The UI is viewing like 20 rows at once, and as you scroll through the entire thing, it'll have to grab different regions, but on each frame of the UI you're actually only reading however many bytes. Basically you only need to be touching a very small amount of that. It's a relatively simple windowing problem. How it interacts with like the watch window being like a tree visualizer is a little bit complicated. because in effect, it's not a simple like, okay, you just have a giant list. In watch windows, it's a little bit more complicated than that, because you have it's a hierarchical kind of list of rows. So if you opened the 1 million element array and then scroll to the middle and then open another, it's an array of structs. You go to the middle, expand the struct has a pointer. You're like, this pointer points to another million elements or something. You expand that. All of that can happen. And so it's a little bit complicated. So I've spent a lot of time making sure that is like as smart as possible about what it's reading and stuff like that. Let's see what else. Trying to think of like other performance things that could go wrong. It's really hard to say because the low-hanging fruit is so low. Like if you run Visual Studio, you would think that almost everything is a bottleneck, but it's like, but there's really
that's why I'm asking. Like you've made this tweet with like, see, this is the Visual Studio that is opening up, right? And this is like, I'm already in the program stepping through the instructions. So like, this is why I'm wondering like, what are the real bottlenecks? Like once you were doing this correctly, like what would be the problem? Like if, for example, Unreal Engine style project with like the debug information is like just huge and you need to get around it. Is this like the problem?
Okay. So that's a really good point. That is a problem. In fact, there is another problem here that's kind of, once you get into the large code base stuff, it becomes a whole nightmare of its own. Okay. So one of the big problems is, in Unreal Engine projects, they have like several thousand possible DLLs might be loaded. Like, it's a lot. It's just a lot of DLLs. And what people have to appreciate is like, if you have a breakpoint placed on a line of source code, what does that fundamentally mean? Well, it's basically saying there's some line in a text file. You put a breakpoint on that line, and you're like, I want the program to stop when this code reaches here. How does the debugger do that? Well, using what we've covered in this conversation, we can kind of figure it out. It's like, okay, source code file path and line number. Let's look up into the debug info. How do we map that to instructions? Well, it's like debug info is per module, right? It's per DLL or per executable. So we can say like, okay, well, this source code file path and this line number, we can look up into this table structure, find out which addresses inside of a module, which relative addresses inside of a module will correspond with that source code. Now, what this means is that this mapping could correctly occur for every possible DLL that you load. So for example, let's say this is a header file, and this header file includes inline functions or just static inline functions, like something that is generated in all of these modules, stuff that's not in only one DLL or whatever. It's in some header file. You put a breakpoint in this function that's included everywhere. In principle, the debugger has to support this case where it's like, this function could be called from any of the modules that are loaded. So if one module is loaded and it has debug info, and this breakpoint on this source code and line number does map to an address, then the debugger can place an int3 instruction there to wait for some thread to hit it. But it's not done, because that mapping can continuously be made when subsequent DLLs are loaded. And so what this basically means, and so the other thing that happens, so you load a DLL. So what this looks like is the debugger is notified that the program has loaded a DLL. The program is stopped. So the debugger, it knows it's loaded a DLL. It maps that DLL to some idea of where the debug info is stored. It has to load that debug info and resolve the breakpoint to addresses before it continues allowing the process to run at all. And the reason why is because even if you expect more DLLs to be loaded and like more stuff to continue loading before that code is hit, the debugger doesn't know that. That breakpoint could be hit before other load libraries complete. Like it could be hit at any time. So anytime you resume the child process, the debug process, anytime you resume whatever you're attached to, you've got to have all your breakpoints resolved. You just have to have them ready by the time you resume the process. Now, in a project like many that use Unreal Engine, you have 2,000 plus DLLs or whatever. What this functionally means is when a debugger sees the very first DLL, it cannot simply tell the Unreal Engine program to continue loading DLLs. Instead, what it has to do is take all of the breakpoints that are set, load the debug info completely, map all of them to addresses in the module that was just loaded, and only after it has placed all of those traps can it continue loading DLLs, or can it resume the debugging process to continue loading DLLs. Now, what this means, maybe that's like kind of in the weeds. What this functionally means for a debugger is that DLL loading is serially dependent. So DLL loading and debug info loading is all 100% serially dependent if any breakpoints are set at all. And so if you put just one red circle on any line of source code, the debugger has to completely load the debug info for every DLL that comes in before any more DLLs can be loaded. Just period. Because what's a DLL being loaded? Like, what is the code that's doing that? It's just regular code that's calling load library on Windows. And so in order to see the new DLLs that are being loaded, you have to resume the child process. But you can't resume the child process until you have the breakpoints resolved. So it's like how people know this about like linked lists versus arrays, right? It's like with a linked list, you have a chain of serial dependence. You've got some node in a linked list, and before the CPU can even begin like fetching the memory for the next node in the linked list, it has to get the first node first so it can read the pointer and then like advance or whatever. It's like that. It's that serial dependence problem with DLL loading. So in a code base like Unreal Engine, this like enormously can harm initial load times, because the debug info is it's not trivial to parse, really. Like if it's in PDB, it's definitely not trivial to start using. Now, because we convert it to our RDI format, we design that format to be as trivial as possible to load and parse. So it's like, if you have all of your RDI files, it actually is very, very fast to resolve all the breakpoints. You can just say like, it's very simple to just map an RDI file into your address space and do the quick lookups for each breakpoint, basically, and then just resume. There's very little actual work that has to be done, but to convert a PDB to an RDI file is very expensive. And for other debuggers, if they're not using the PDB like a database format, which is what it is, it's literally called, excuse me, it's called a program database is what PDB stands for. And it's supposed to be this like database format where you kind of map it into memory and you like make queries on it and stuff like that. Very not like what people want to treat debug info like, which is like a file format that you completely parse. And so debuggers which have this sort of parsing structure to like Remedy does this, for example. You'll see if you try to run an Unreal Engine project on it, it will like, and you just see how much memory it'll start allocating. It'll begin like very quickly. Remedy will be using like 20 gigabytes of memory just from parsing the initial DLLs or the initial PDBs for the DLLs that Unreal Engine loads. And that's because it's just grabbing each PDB. It's like, okay, time to parse the entire PDB, and I'll just do a full parse of the entire PDB file. And that's kind of what our converter has to do, because our converter has to parse the entire PDB file, convert it to our own structures, and then bake that down into an RDI file. And that's not free, and especially for Unreal Engine sized code bases. And when you do that per module, it can like pretty drastically impact startup times. So that's a big problem. Yeah, I mean, hopefully I explained that to any sufficient degree, but it's yeah, that's actually a really big problem. I hesitate to say that's a debugger bottleneck, because it's like code bases are just getting so arbitrarily large and complicated these days that it's like, I don't know, man, is it my bottleneck or is it yours? Like, I don't you know what I mean? But yeah, so that's one of the things I've got to deal with, for example.
I wonder how would it look like also on the automotive side of things? Like the automotive software can be like 100 or 200 million lines of code.
Yeah.
Let's say per vehicle. Like, I don't know what's the size of Unreal. It has a lot of DLLs. Maybe it's not the case for automotive software. but like still, I wonder like. Okay, now that's a tangent. Let's skip that.
Yeah,
Okay.
I did, for example, spend a lot of time. I'm not really a performance programmer, so I didn't spend time like counting cycles for the
Yeah.
converter or anything. But I did do a whole pass over the conversion, or I basically rewrote the entire converter, um, uh, and basically just to parallelize it. So just taking all the problems taking all the subproblems of the whole problem of PDB to RDI conversion, finding all the things that are very trivial to parallelize. Like what can we parse in completely asynchronously? What can we generate asynchronously? How do we bundle all of them at the end after they've been done asynchronously? How do you do that deterministically? I did one big pass over the converter to just make it perform much more quickly, using that kind of thing. But I didn't do quite the, I'm not, like I said, I'm not a hardcore performance programmer where I'm like really grinding down the cycles of some conversion code path. It was really more of like a multi-threaded kind of problem. But that's coupled in with that DLL loading thing. In general, it's like how quickly can you produce the parsed representation of the debug info, if you don't want to treat PDB like a database format and couple all of your debug info to it, basically. But
Okay. I would close the debugger section. Do you have
Okay.
anything to add on top of that? I think you outlined a lot of the internals, how to work, and also some sort of the common issues or problems with it.
Yeah, I think the last thing I would say is like, well, on the DLL loading thing, big thing that's big news on that front is basically Nix linkers is actually working, and you don't have this conversion cost at all with the linker, because the linker can produce the RDI file just natively, for basically the same cost of a PDB. So instead of producing a PDB, you just produce an RDI, no conversion cost whatsoever, and this is just much faster. So that's the last. Yeah, that's a good spot to end. There's tons of stuff to cover in a debugger. There's so much. So that's probably a good place to wrap that tangent up.
Yeah. Okay. I have a couple of, let's say, less technical questions before we close this conversation.
Okay.
You spent a lot of time working in C and C++. I didn't do that much C and C++. I know how to get around it, but all of the newer alternative languages, Odin, Jai, or like Zig, seem much more appealing. What would you say for new programmers joining in, wanting to do low-level work? Is there argument to like save C++, spend 10 years of learning all the history, what to do, what to not to do, even though it's available, and like, what would you say?
So I think what I would say is, a programming language is not just a language design. So I will be the first person to say that, well, certainly C++. C++ is not it's not a well-designed language at all. C accomplished many important things, but I think you can clearly see its age. It has a lot of design flaws. The build model is ridiculous. The type system has various rough edges and like bizarre rules and implicit conversions, and the syntax is busted and unnecessarily difficult to parse. It's like there are problems with C. There are a great many more problems with C++. All of that is true. But for me, the reason why I, for now, will stick with C is because, like I said, a language is not just the language design. It's called a language because it's what people speak, right? It's what different tools and what people speak. And when I say that, I don't mean to pigeonhole myself into the readability argument, because I can read Odin code, I can read JI code. None of that doesn't matter too much to me. What matters more is the fact that people have poured like decades and decades of very expensive engineering resources into C and C++ tool chains and debuggers, which are suited specifically to C and C++. like I said, the debug info is not language specific, but there are many features in a debugger that have to be language aware, to one degree or another. So yeah, compilers, compiler backends, debug info generation. Did I say debuggers? Maybe debuggers, editors, sanitizers, like educational resources, libraries. Like there's so many things that people have done that are to one degree or another coupled with a programming language. And so the benefit that you get from a language is that you're able to like communicate with all of that work that people have done directly without any friction. So the reason why I'm a little bit apprehensive, I guess I would say, about new languages is that if you move to a new language, the design surely will probably solve some of the issues with C. Certainly, I think Odin and JI are like the most favorable for my style and my opinions. Like I feel like Odin and JI are basically the closest on the map. And I think Odin certainly has a better thought through design than C does, for example. But switching to a new language means you're sacrificing potentially many things. So Odin has one compiler that's LLVM based. This compiler is much younger than MSVC and Clang and GCC. So what? Not to single. I don't want to single out Odin at all. It's just the one that I would say most familiar with. But I guess what I'm saying is that when you switch languages, especially to newer and less mature languages, you're potentially running into in the future compiler bugs, debug info generation bugs, various instabilities, missing foreign function interface support. Like, if there's some native API you need to call and they don't have bindings for it, those APIs are all exported by the operating systems in C for the most part. And so it's like, okay, got to go write bindings for it now. Like you'll hit potentially many problems when you actually start switching to these languages because, like I said, a language is not just a language design. It's not just a compiler. It's also all of the things that editors expect. It's all of the things that debuggers expect. It's all the things that sanitizers expect. It's all of that. So you're potentially compromising a lot. And it's not that I want to be stuck with C forever. It's that I think the cost of switching has to be worth it. And so I think currently it's too early in these new language like histories for it to be really worthwhile to me. Furthermore, I think that the development of a new ecosystem all using a language, it's as if you it's as if you built a house on a foundation and you're like, okay, let's change out the foundation. You know what I mean? It's like, you can't just do that. It takes a long time to actually build the house on top of the foundation. And so for me, it's like I look at the problem of building a new language, like building a new house on this new foundation. And to me, it's really important that all of the effort that goes into building that house is not wasted on something that is roughly approximating the same experience. So, Odin is definitely a better language than C, I would say. Like, given what I know about it, it's probably much more pleasant to write. Will it be more pleasant, given, perhaps lacking debugger support, potentially debug info generation bugs? Maybe it does. It is currently coupled to LLVM. LLVM has compile time problems and stuff like, which is why I don't use Clang on Windows, for example, for debug builds at least, because it's just too slow. So there are some problems like this. So I guess what I would say is, for me, the project of building an entirely new computing ecosystem, if it turns out to just be a cleaned up C, I'm not sure it was worth it all along.
Okay.
Now, personally, I don't want to be stuck with C forever, but my ideas expand beyond like new languages. I think if you're gonna change the ecosystem, you might as well reevaluate more than the programming language. So, for instance, why are we storing code as text files? Like, why are we even editing text files? Why is this the base format for all of our tools? It seems like you could get remarkable improvements by reevaluating the core source code format. Seems like editors could be much more powerful if they can work with the structural representation. This is what all editors have to actually do eventually anyways. Like, they're all trying to build their own internal abstract syntax tree structures, and they're kind of hamstrung because producing that abstract syntax tree is both computationally and like to actually do it as a programmer, it can be very difficult. And then you also have to reverse all of the changes to that abstract syntax tree back to text, and that is a huge ankle weight to fancier editors, I would say. And so I would think much more that direction. It's like if we really wanted to, from first principles, completely reinvent the programming experience to make programmers much more effective, much more efficient in their day-to-day life. You know, why would we end with just, you know, the format that the compiler and that the editors expect? I'm sure there are wins there. I know that C has problems, but yeah, like I said, to me, the cost has to be worth the transition, or the benefits have to be worth the transition cost. And currently, I would say that they're not. So, for new people who are looking, you know, I don't care what people do. Like, people can use whatever the language they want. If people are interested in Odin, like, or JAI, go try them out. If you have access to the JAI beta, you know, go for it. For me, and I think that's fine. I think that's totally fine. For me, the reason why I stick with C is because I'm trying to think about my code bases in a much more long-term kind of way. I'm trying to think about, like, which tool can I reasonably depend on being here in 20 years with solid tooling support for the whole time. And, you know, that's important because I'm going to spend tens of thousands of hours on this code base for the next however many years. And so it's really important that that work, you know, doesn't rot in value. Like, it's really important that I can rely on that work being there. And what's the future of Odin? What's the future of JAI? Will I have good tooling support in them as I, you know, would switch them? Will the tooling always be there in 20 years? Like, I don't know. In C, it's like, yes, it'll be there. Like, there's so much money riding on C and C++ compilers and tool chains that it's like, that is not going away anytime soon. So it's a very safe place to put your code. With these newer languages, it's like, they're very cool in many respects. There's a lot of cool ideas that they've done. People should try them out. I don't have any problem. I don't have any problem with anything that people want to do, obviously, but you know, so people should try them out. People should check them out. I have talked about this to some degree because it's like, I'm trying to think about what's smart for me to do with my code bases. And so I'm not just going to switch to any arbitrary language right away. And so I hope that is useful for people who are trying to think more in that direction, I guess. Because, yeah, there's a lot more to a language than its design or than its, like, compiler. So,
yeah. Okay. You are writing a blog, and I was wondering whether you're documenting things to help yourself and, like, to kind of, like, put this into writing to understand what you really are thinking, or is it more towards helping other to understand, or maybe do your part to kind of like let people learn more about how to code? What is the reason behind the blog?
I think it's probably both of those things. I know that's not like a satisfying answer, but I think writing is very useful for both of those things. I really like discussing things with people, so I like putting out information that I've gathered that I feel very confident in. But the other side is, like, if there's information I'm not confident in, writing is an enormously useful tool to, like, straighten it out in my head. And, like, you know, how much can I write about this, and how well can I explore the contours of this idea? Those are, you know, if I can write a very long blog post about something and really sufficiently explore an idea, then I feel like after I've written a post like that, I have a much better grasp on the concepts. And the dual purpose is that if I did a good enough job writing it, other people get that same benefit. Like, they also have this, they also have at least one window from my brain, which may or may not be useful to them, but they at least have one glimpse into the problem that could help them a little bit. And I think that's broadly a useful thing. It's useful for me because, obviously, like I said, clarify my thoughts, concretize my thoughts, and like flesh out my thoughts, throw away the parts of thoughts that I like while writing. I'm like, no, that's dumb. Like, don't. That's a bad part of the idea. Like, throw that out. If it's embarrassing for me to type, then I'm like, oh, bad idea. Actually, like that's not good. So that part's very useful. And just for the sake of like, for other people who are in kind of the same camp as me, of like, you just want to make good software and think through it in a very first principles first kind of way, like not adopting all of this like, frankly, a lot of snake oil from the industry, like of just how to do things in bizarre ways, like not adopting that, like really trying to think through fundamentally, what do you want the computer to do? How do you do that in as good of a way as possible? Bottom up, basically. For people in that camp, I think it's useful for them to just share information. And I think if it's true that we're right about how to make software better, then that's actually going to be better to like grow that movement of people as well. Like, if we put out all this useful information about how we're building software and how we think about it, and we do build useful and good software with it, then maybe it'll be a good like beacon of information for newcomers, maybe, who have enormous amounts of programming potential. Which ideology of programming is really going to win them over? Is it going to be like, are they going to go like watch a bunch of Uncle Bob talks, or do we want Casey's videos to be online so that they can go learn like how to actually build useful stuff? And so I feel like I care a lot about signaling information to people, and like informing them of my experiences to save them the trouble, basically, because obviously nobody can build everything. Like, I've spent 4 years of my life working on a debugger. I couldn't have spent those 4 years working on a completely other complicated problem. So for people working on those problems, I'm happy when they have a blog post about it. And for people like them, I hope that they're happy that I have posts about my stuff on the debugger. So yeah, long way of saying both, I guess.
And you do stream as well, right? You stream yourself code.
Fairly irregularly. Like, I'm not a regular streamer, I would say, but whenever I find some time to do some personal project work, I assume it's because the debugger is open source. I assume I could probably stream working on it, but I don't know for sure. but yeah. So anytime I find some time to work on a personal project, like I'm working on a game, anytime I find time to do that, I sometimes will like to stream, just programming. Which similar feeling for that too. Like, it's useful for both me and hopefully for people watching. So,
what game are you working on?
So I'm working on you can think of it as like a traditional adventure game, top-down dungeon crawler kind of structure to a game. But the part I'm trying to explore gameplay wise is it's trying to support procedural crafting. So usually crafting systems in games are like a fetch quest where you go gather a bunch of ingredients and then you like go to a crafting table and you're like, okay, you have like iron and wood so you can make a sword. You click the button, you get the sword, and the sword is just another item that an artist went and painted, and now you have the item. Like, there's a bunch of stats for the item that somebody had to design and all this stuff. In this game, what it's trying to be is procedurally doing all of that stuff. So I hand designed the actual ingredients, but in order to produce the effect of a sword, it's actually like, you can think of it almost as like a little mini programming system where it's like, if you wanted to, for example, produce the effect of a sword, you could have, a wooden stick for the handle, and then, sharpened iron as like 2 downstream nodes. It's like a little canvas graph kind of crafting system. So you put the handle, you put 2 downstream nodes, and let's say I wanted to add, for example, a fire enchantment to this sword. Instead of needing an artist to go and build, like, okay, make a fire enchanted sword, make the art for that, and then let me go add the gameplay code for like, here's what a fire sword does. Instead, what I want to move that into is like just all the procedural crafting system. So in the crafting interface, you could also add like, there's like a fire gem ingredient, which you can arrange that onto the graph as well. So you could have like, okay, I've got my sword, let me add a fire enchantment to the top. And now let's say you wanted to have the sword shoot, instead of just having a fire effect on its hitboxes, maybe instead you wanted it to shoot a fireball as well. Now there's a different kind of ingredient called it's a wing gem. So it's a gem shaped like a wing. You can also equip that to the top. So you build out this graph of effects. So you can have like, okay, you've got your base sword structure. Now you can add a wing gem, which produces flight, which is a projectile generating thing. So projectile generating, then fire applied to that node. And so that actually causes a fireball. Now if you wanted, for example, the sword to shoot 3 fireballs, you can do that too. It's like just, okay, sword structure, 3 wing gems downstream of the tip of the sword, and then fire gems on all of those, and now your sword will shoot 3 fireballs instead of 1, instead of also just being a regular sword. So the idea is for like all of those kinds of fancy gameplay effects to be completely procedural within the crafting system, and then just taking that idea and applying it to like traditional Zelda style adventure kind of structure. So it is a 3D game, but it's a top down kind of simplified 3D game. So
How much time do you have weekly to work on it?
not enough to make tons of progress, but how much time do I have is different than how much time I've been disciplined about spending on it, is I guess what I would say, because it's really hard to program a game after you've spent 40 hours programming a debugger every week. So it's been really slow for me. On a good week, I might get 10-15 hours of programming on it in a week, but that's pretty rare, honestly. Like I can get if I try to do too much like that, I'll get burnt out pretty quickly. So I try to be pretty relaxed about it, and just it'll make progress when I make progress on it, basically. But
Okay. You also have engaged on Twitter, and you do engage often in and saying what Casey's saying what you're saying, for example, often sparks, let's say, negative attention. And I wonder, like, what did you take out of these Twitter drama battles so far? Like, have you learned something, or also like both on the sociological level, but also like on the programming level?
So I think one of the big things I've learned is that when you are interacting on a system like Twitter, you are not engaging in rational debate. Like, that's not what Twitter is. That's not what it's for. And I think people take Twitter very seriously in that way, where they're like, I'm engaging in a debate of the ideas, and I'm trying to get to the bottom of things. And the reality is like, that's not what Twitter's for. That's not what it's designed for. That's not how anyone uses Twitter. And maybe that's a shame. But I don't, how you have at scale social media with productive conversation is like, I'm not sure that's a solved problem. So I guess what I would say is that when you're on Twitter, when you're interacting on Twitter, you are participating in basically a contest of signals between different people. So people are signaling. That's all Twitter is. It's just constant signaling of just random viewpoints and reactions to stuff, and that's all Twitter is. It's just this massive chaos nest of that kind of stuff. And for me, it's really important that people who, I won't say that I'm like an expert and that I 100% know what I'm doing in all cases and all these things. I mean, I think I've learned a lot about programming. I think I've become a pretty good programmer. I still have a lot to learn, of course. And I think that'll always be true. But I think that it's important that people who know what they're doing, I think it's important to not just become jaded with the idea of signaling things that are important to you. So, and the reason I say that is because beginners cannot evaluate rational arguments about things. And they can't evaluate rational arguments not because they're dumb or because they're not smart. It's because they don't have the information yet. It's like a chicken and egg problem. It's like, how does a beginner become an expert and begin evaluating rational arguments about programming techniques or, whatever you want to talk about? How can they start evaluating these arguments? It's like, well, they have to become an expert first. But how do they become an expert at all, like, to begin with? Like, who do they follow? Who do they choose to follow? So I think it's important that people who are doing stuff that's good, they should signal about it. They should put signals out into the void so that people can see, like, here's someone who knows what they're doing, and here's how they feel about this stuff. That can let them gauge what ideas are useful and what ideas are not useful. And I think that when you approach it from that perspective, first of all, it kind of forces you to approach Twitter a little bit less emotionally and a little bit less like personally, and it lets you engage with it more like an engineer would. And it sounds weird saying that because it's not about engineering. It's like social engineering almost, but it lets you approach Twitter in this way that's like, I think, much more productive, where it's like, what are you putting out to people? What signals are you putting out there, and what are people going to take away from it? And I think that can be remarkably useful in, for example, attracting people to a certain set of ideas. It can be useful to say, like, here's the kind of work that I do, and here's how I feel about, like, you know, clean code or whatever. Like, that's a very useful thing for people, because I think it can help not lead them astray about certain things. And I think the other thing is, like, I think that when people who know more what they're doing, when they choose not to participate, when they choose to sort of disengage altogether with things like Twitter or YouTube or whatever, when they choose to do that, it's like, you're not actually winning the battle by doing that. Like, there is a battle of ideas going on, and I think that all you're doing is, like, forfeiting the terrain to people who, yeah, are just shitposting and are just, like, just saying pure nonsense or selling snake oil, like there is so much of. I think that you're kind of ceding the territory to them, and I think that, I don't know, that doesn't seem satisfactory to me. I would like to provide my genuine reaction to things, and so that's all I really do. It's if I respond to something on Twitter or something, I'm not doing anything clever other than I've kind of tried to understand the meta of why I'm doing it, but all I'm actually doing is providing my genuine reaction to stuff and trying to say it in, like, a succinct and maybe entertaining way. But it's I'm not trying to be dishonest. I'm trying to provide, like, no, this is actually what I think about this particular thing. And you know, if in theory, if I do useful work, then people have one more data point about, like, well, this is what someone who does useful work thinks about this particular idea, and maybe that can help suss out some of the nonsense and some of the good ideas too. So that's I guess what I would say about that. The other thing is, like, it's when you learn to not make it so personal, it's pretty fun. Like, it has been unpleasant. It has been very unpleasant to me before, to be clear. People can be pretty vicious, but I think if you learn to sort of disconnect with it personally and always maintain your personal relationships, like, more than you care about Twitter, for sure. and if you do that, you can approach it in a pretty healthy way that also, for example, can be useful to, like, gain a following, promote projects, promote an idea. Like, all of that stuff is very useful. And I think it's not that I appreciate, it's not that I think that it's unfortunate that there's this, like, completely adjacent system to programming called Twitter where everyone is just flaming all the time. It's like, look, man, the bad guys from my they're bad guys from my perspective. They're using it too, so we've got to use it to get more people on our team, and to, like, organize and build good stuff and kind of, like, I don't know, revitalize at least some small part of software and make it good again. So yeah, that's kind of how I feel about that, I guess I would say.
Make it good again. Let me touch on that. What happened? How you see this? There is a lot of things, for example, materials about clean code, how to write code. I learned programming through Java mostly. So clean code was like the book, even though it's not about, like, Java JVM, kind of how Java bytecode looks like nobody talks about that. It's more about, like, how to structure your methods. This should be 30 lines long and things like that. And how did you learn? You kind of said that in the beginning, right? Like, you learned through Handmade Hero, a large portion of it, but also, like, how do you think this happens, that these ideas stick? Like, there are people that learn through Handmade Hero and they kind of escape this vortex, but, like, everyone else is like, ooh, let's now measure the readability with, like, AI tool to make sure that your code is readable because it has, like, less than 30 lines. It's like, dude, please.
Yeah. No, I mean, it's a good question. I think that the most charitable interpretation is that for a lot of those things, they made sense in some kind of context. And then they kind of devolved through a long chain of like telephone. So the idea of this happened with um, like go to considered harmful, for example. It's like that. This happened with that. It's like when structured programming was new and people were just like making large spaghetti soup of go tos going everywhere, and like nobody was really like on board with the idea of structured programming yet. Maybe it made sense to say something like go to is bad, like use these new control flow constructs, like they clean a lot up, like that kind of thing. But I think I think that in a historical context certain ideas can make sense. Like the 30 line method thing, though, I mean, it's really just hard to find a charitable read. The reality is like I think it's a mix. I think that there are some good ideas that made sense in context, and through the game of telephone, people misunderstood or people over applied these ideas. A lot of noise was introduced into these ideas over time. I think like a lot of that happens. There's also a lot of just like bad actors, and I can't find a more charitable read than that for a lot of cases, because I genuinely think that they're preserving something other than like software quality or good ideas for programming or something. I think in a lot of cases people have careers built on like consulting services that they provide to companies. They've written a lot of books about certain topics. They have done all of these things, and if these ideas fail, they have spent like 30 years of their life like promoting these ideas, maybe because they even started somewhere charitable, like I was saying. And so I think that like people really connect personally with ideas, and so I think that people develop vested interests in like continuing them, even if they're completely inappropriate, and if they're very bad, and if they don't work. Like I've talked a lot about like arena style allocation, for example, as being like a useful way, or it's a useful construct to sort of organize the way you're doing memory allocation so that most stuff turns into a linear allocation, just a simple bump allocator. And if somebody came out and like with like just a completely groundbreaking allocation style where that was just like way simpler to program, way more performant than arena. It's really hard for me to imagine this, because arenas are just almost no code. Like the reason why I've written so much about them is because there's so much unlearning to do. It's not that there's so many new concepts to learn. It's that there's so much stuff that people have to forget. And so I think it's hard for me to imagine this happening. But let's say theoretically it's like you just had this completely new technique of doing memory management and organization of memory allocation, and it just blew all of my memory management code like out of the water forever. I would have a hard time. Like I can see me in that context being like, man, like I wrote all this stuff, I did talks on arenas, like now those are completely invalidated. Like would I be incentivized in that moment to like really double down? I would hope the answer is no, but I can certainly understand why people would say yes, right? I can certainly understand why some people in that context would double down and would stay connected to their ideas, which were maybe never that good to begin with, or maybe they've become stale and out of date. Maybe they're conflated with a lot of noise. Maybe they're over applied. Maybe they're over extrapolated. Like who knows really? But I don't know. I think that the root cause of this, it's really hard to understand like why software seemed to be so much better before and why it's gotten so much worse in so many ways. But I think that at the root cause, there does seem to be a problem of like using something other than a standard of just complete quality to measure things. Like people make a lot of excuses for mediocre results these days, and I don't know exactly why that is, but I think for me that's never really felt good enough. Like I don't know. I feel like ultimate progress is made by progress in making software better would be like uncompromising. It's like, no, this can be easier to program, and it can be faster, and it can be like almost no code added. Whereas like a very dominant way of thinking about problems in computing today is like people over apply this idea of trade-offs. They're like, well, solution A can be readable, but solution B can be faster. You cannot possibly get both. It's like, no, there's actually solution C, which is both more readable, easier to write, and it's faster. People like think that those solutions can't exist, when I feel like the reality is that they're everywhere to be found. And so I think people have to get out of the idea of like, when you're building software, you're not forced to accept just mediocre results. I think it's like, I don't really know, and I don't know why people are so intent on accepting mediocre results, but that just seems to be the situation. I don't know.
And on that topic, there's a conference coming up, Better Software Conf, and you'll be one of the speakers. Do you know what you'll be talking about?
I'm trying to figure it out. So one of the coolest parts about the debugger is the visualization engine system. So the fact that I've successfully collapsed all of the visualizers in the debugger down to being like fairly general purpose. So for instance, if you open up a source code viewer in the debugger, that is the identical UI that you get if you evaluate a string in the watch window and apply the text visualizer to it. So if you put something in the watch window, you say visualize this as text, and you expand it, it'll come up with a little mini source viewer basically for that one string. And so that can apply to memory, and because it is used for the source viewer, you can also apply it to files. And so really what I've done with the evaluation system and with the visualization system is the debugger now functions as like a general purpose data visualization UI basically. So it's not, a lot of work to do before it's like really solid for that, but you can use it as a hex viewer now for like files, because the debugger UI exposes the ability to evaluate not only things from processes, but also things like files. You can evaluate a file path, and it'll say, oh, this is a byte array of, this many bytes, that's however big the file is. And you can attach visualizers to it just like you could with memory from a process. And so if you take, you can evaluate a file, you can say, apply the text viewer, then you get the source viewer basically for that file. You could do a memory viewer, you get a hex viewer for that file. And all of these visualizers can be applied to anything. Oh, disassembly as well. Disassembly is also this. It's just like, you could apply it to a file, you can apply it to a function evaluation. If you say, okay, evaluate the function foo, disassemble that, assume it's an x64, and then disassemble 1024 bytes of it. Show me what the disassembly is there. That disassembly view that you get when you evaluate that and visualize it that way will be identical. It'll have all the same features that the disassembly view proper has in the debugger. Like you'll see instruction pointer arrows, you'll see line info, you can copy and paste. All of the same features keep working. And so I've successfully collapsed all these data visualizers down to be like fairly general purpose and pretty powerful. And I think I'll talk about that. Because that's such an important system, I think, long-term for the debugger, that it really feels like magic. So I think that's probably worth talking about. If it's not that, it might be some other, maybe a little bit higher level, like maybe a whirlwind like crash course through debuggers or something like that, or through the RAD debugger, maybe just to ground it. Something like that. It'll be something debugger focused, because that's obviously what I've spent the most time working on. And but I think the visualizer would be a really cool system to cover. So yeah, that's what I think, but we'll see. I've still got to plan it out a little bit more.
Okay. Yeah, I hope that the conference manages to inspire people, because I think like information is out there now, and you can get it easily, right? What you really need is like motivation to get it, and to have the motivation you need to be inspired. So I hope this talk also does that, because you shared a lot of information, and it's so cool to see somebody so into this and figuring this out as they go. It's so good. Thank you so much for joining me. Let's shout out, by the way, Digital Grove is the name of your blog, digitalgrove.com, or what's the URL?
The URL is just my first initial and last name, so it's rfleury
Yeah.
rfleury.com. Yeah, I probably should get digitalgrove.com, but I have not. but yeah, so
Yeah, and the project you're working on, RAD Debugger, is open source, so anybody can look up the source code, see the Handmade Hero resemblance in
Yes.
places.
yeah.
And
Well, you mentioned inspiration. I tweeted this the other day actually. Everyone should go watch the Handmade Hero announcement trailer. It is so magical. It actually shows you like it just throws away all these ideas of like, is this business efficient? Is this, are we using libraries responsibly? Like none of that even comes into the picture. It's like, no, we're going to do this because we love software. We love making good software. We're going to do it from scratch because we care about every little detail. And it's just, so people are looking for inspiration. That's a good stop on that journey too. Cause, man, that I still watch that trailer and I'm like, man, this is totally why, like, all of this is worth doing. So it breathes fresh life into my burnout stages. Every time I'm feeling burnt out, it's like good to go watch that trailer to be like, yep, this is why. So
I watched it 2 days ago for the first time, and
Oh,
I
wow.
was shocked because like you were tweeting this, but for some reason like I was lost there and like didn't look it up, and I was like, I was moved by
Yeah.
this trailer done like 10 years ago.
Yep.
Knowing all the stories of people that were like, oh, this is what pushed me to do this. This is why I realized I can do this. Like all
Yeah.
of these histories of people that were like building their life upon this project, and
Yep.
it's also had such a cute trailer, so inspiring.
Yes,
Okay.
definitely.
Thank you so much, Ryan. Thank you so much for joining me and inspiring talk. I think it might be the longest or second longest, but
Nice.
the other candidate is were two people, so like you get the award of
Wow.
longest time speaking.
Well, that's
single
amazing.
member.
It might be because I ramble too much, but but yeah, man. I mean, it's been my pleasure. Thank you so much for having me on.
Thank you so much for listening to this episode of the Game Engineering Podcast. Don't forget to subscribe on YouTube and follow on Spotify and other podcasting platforms. See you in the next episode.